Αυτό το πρώτο.
Και εμένα.
Όχι, δεν μπορώ να φύγω μπροστά. Εμένα είναι 16-9.
Άρα, τόσο είναι πρώτο.
Πρώτο είναι το μάθημα. Κάνουμε την εισαγωγή.
Να, τους έκανε
μετά είναι οι δύο ειδικές μας. Μετά είναι Δίπλα σου. Τι είναι? Αλλά δεν είναι το stream. Και μ' ακούνε τώρα εδώ? Όχι, θα πάω να κάτσω εκεί.
Έλα από εδώ.
Επίσης τώρα έχω και στο μικρόφωνο του stream, οπότε... Μπράβο. Μας ακούνε international stream, national και εγώ.
Δεν καταλαβαίνω.
Να το βάλει ένα Google Translate, speech lanes.
Η αλήθεια είναι αυτή. Ποια?
Η μόνη επιλογή είναι να μιλάμε καρτισιόν.
Έχουμε και άλλους κρατήσεις. Έχουμε να κοιτούμε μιλάει τσακό. Ποιος μιλάει τσακό? Εσύ. Α, νόμιζα ότι μιλάει κι άλλος. Για να μην μας ακούνε στο stream. Δεν αβάχω. Γιατί μου λέγαμε πριν αρχίσουμε ότι η καταπίσια είναι λάθος λέξη. Στο ήταν μας δει. Ναι, θέλει.
Okay. Kalimera, welcome. So, I'm here to do the welcome talk, and like the opening ceremony is a bit bold for the thing I will do, but okay. So I'm really happy that we are here in person after so many time. Anyone that been here in open source CubeSat workshop in the past? Okay. Do you remember when was the last one in person? 2019. Yes, was 2019. 2019. 2019. So it was like 6 years ago in Athens in a different venue. And from we have done one or two online events, and wanted to reboot the in-person events for like 2 years now, and we had some we were I think we couldn't find the time to set up this, but we want to reboot these events and like make the community like meet again in person and talk and do wonderful things. We also looking ahead to like expand the area of the event and like include not only CubeSats but like since the last event we have also built pocket tubes. The community have built microsats, satellite buses, tools for open source tools for space, open source tools for ground segment, like for midstream. Like the whole ecosystem has become bigger and bigger. So we want also your ideas to try to make the event more more broad and include more stuff about the open source space in general, not only CubeSats. Now about this event, like talks are at 20 minutes. Some people are already complaining. They want 40 minutes or so. So try to be quick on your time, like presentations. We are saying like 12 minutes for presentation, 8 minutes for Q&A. There are 2 meeting rooms on the back, so if you want, like for ad hoc meetings or project meetups, or use them like whatever you like to meet. And also we have slots for lightning talks at the end of the second day. Coffee is available outside and also lunch break. And contact organizers, like we have the same tag as you have, so you cannot find us. Now you know only my face, so contact me, I don't know. Fred is also here, Nicoletta is also here, Yorgos, Manoglis. And we have today at afternoon, we said 8 o'clock, we have a social event at hackerspace.gr. We will find the info on the website or contact someone, like a relaxed informal meeting with some like beer, food, sodas, I don't know, yeah. And also we want to create a safe space, so there is a code of conduct in place, and there are Nicoletta and Yorgos are, I have put their faces here, so you can find them if you like. So contact them if you have any issues. Enjoy. So this was for me, and we can start the talks, I think, yeah. Thank you. So I will also introduce Freddy, which is the first talk, the first 2 talks for today. And Freddy is a colleague of me. In the last physical OSCW, he said that he is Satnox. So, so Freddy he will talk about Satnox, the State of the Union, and also has a second talk about SSA using Satnox. Freddy.
Okay, give me 1 hour to set up presentations. Ακούγεται. Test. Okay. Cool. So, my name is Alfredos Damkalis, or you can call me Freddy. I'm one of the developers and operators of Satnox. And today I'll give you a short update for the last year, where we are and where we are going to go. First, for those that don't know SatNox project, a quick overview. SatNox started as a project for automating ground segment operations through a network of satellite ground stations. What we do today, what operations we do is to have telemetry and telecommand and control capabilities on VHF, UHF, L-band, and S-band. And also we gather telemetry and data visualization. We also have a collection of observation artifacts like data frames from satellites, audio, spectrogram, and IQ data in some cases. We also do perform orbit determination, and we generate orbital data in TLE format. And we also identify satellites and record frequency violations in some cases. What is SatNox? It's an open source stack of software and hardware projects, some services, online services, and a collection of data. And we have contributors from different fields. Like universities, organizations, and the radio amateur community, and all these people, and even individuals or space enthusiasts. So we can split the SatNox project into three main categories. The one is the ground station. That includes the software that controls the ground station, the radio part of it, and the hardware components. Then we have the web and other services, like the network, the DB, and decoders and Grafana dashboards. And then we have the operations, where we schedule observations, and we do satellite identification, orbit determination, and orbital data generation. So let's go through them and see more details. So we have the control software, which is the one that receives jobs from the SatNox network for the ground station, performs the observations of the satellites, and then uploads the observation artifacts back to SatNox network and SatNox DB. The last year, we had a transition to Docker containers. So in order to have better compatibility and accelerate the development of the SatNox client project. And we also do some serious maintenance and bug fixes. For the future, we want to add some missing features in the new architecture to create some new interfaces for the radio part and also for the network communication. Also, we want to support configuration through the SatNox network, and so there will be no need to connect to the ground station at all. We also want to do some changes for compensate the Doppler shift that we observe in satellites. Add a graphical user interface to be more friendly, and also support transmission to satellites. The next component is the radio software, which is responsible for doing all the processing and demodulating of the received signals from satellites using GNU Radio, and also produces all the artifacts that we gather in SatNox network and DB later. The last year we had a transition to GNU Radio 3.10. It also there was a transition in the Docker architecture. There are some new interfaces for sharing the observation artifacts and also control the radio part. And also there was bug fixes and maintenance. For the future, we want to keep up with the latest GNU Radio versions. to create on-the-fly flow graphs for satellites using transmitter parameters. Also improve the current support of transmissions, of modes and modulation of transmissions, and then improve the interfaces for controlling and sharing artifacts, and of course to also support TX. Yes? The question, just to put it in the microphone for the streaming, the question was about if we need real-time communication, let's say, with the satellite through the ground stations and the network and stuff like that. So we are looking on this. Right now, it's not happening, but we are looking for real-time.
Real time. It's like scheduling. When there is a pass above the flight, when the ground station is on the field of view, it just transmits the frame that you have scheduled.
Yeah.
This is a mode of operation.
Yeah, it depends on the mission and how critical is it for having real-time data. Okay, let's continue. The next part is the hardware components. When we say hardware components, we get all the stuff that you meet in a ground station, like antenna, rotators, the electronic components like filters, LNAs, and also kits that contain everything you need. So the last year we had developed the SatNox kit. That we gathered all the components that someone needs to create a simple station. And then we also have some contributors in our forums to showcasing and show us how they develop their own station setups. In the future, we want more development and documentation on the ground stations. Oops. Okay. Then we go to the services. We have the SatNox network, which manages the stations. It's responsible for scheduling the observations and also store, display, and allow us to rate observation results. The last year, we had a transition from using NORAD ID to identify the satellites to SatNox Satellite ID. We had many performance improvements, bug fixes, and maintenance, and also some improvements in user interface and user experience. For the future, we want to support multi-rating for observations results. We want also to transition from waterfall spectrum images to actually spectrum data. Also, we want to automate the scheduling part with some lists that will set the priority of observing and scheduling, and then some general improvements on the API, some statistics about the network itself and its stations, and also improve the documentation for users. Some statistics. Currently, we have around 290 online stations and some in testing mode. We perform around 5,500 observations per day, and we demodulate around 43,000 demodulated frames per day. Then we have the SatNox DB, where we store the information in a crowdsourced format for satellites and their transmissions. We also store some of the data from the satellites that we collect from network and also from third-party observers. And also we store orbital data. The last year we had restructure and document the way that we suggest new satellites and changes for the satellites and transmission entries. So it's more user-friendly right now. Also, we have performance improvements, bug fixes, and basic maintenance, and also improvements in UI UX. For the future, we want to create some new API endpoints that will help us to perform better. Also, we want to have more detailed transmission info, especially the parameters that we are going to use for the flow graphs that I told you before. We also want to create entries for launches that will also follow the crowdsourced logic, and then some general improvements as in the network. Here are some statistics about SatNoxDB. We are currently have around 1,000 satellite entries. We have the last year we had around 2,161 satellite suggestions, for around 4,000 transmitters, and the last year around 2,000 transmitter suggestions. And also we store around 290 million frames from different satellite missions that were contributed by 5,000, almost 5,000 stations. Then next is the SatNox decoders, which is the way we describe the encoding of the satellite frames in a format that is called kaitai.io. And with this structure, we can generate scripts that decode the frames that we receive from the satellites. The last year, we created 27 new decoders. We had some improvements and fixes on some existing decoders. And we had people involved, even from satellite teams, in the whole process of creating the Kaitai structs and the decoders. And from all the DB frames we have, around 43% is decoded. So we have plenty that we don't have decoders because either we don't know how to decode them or because no one has already created a decoder. For the future, we want to create more decoders and involve more people and also improve the process and the documentation. Then we have the Grafana dashboards, where we visualize all the decoded data from satellites. The last year, the dashboards new dashboards were created from the community and also satellite teams, even some before the deployment. So when the satellite deployed, we're there to support the team. The dashboards are used from satellite teams for further analysis of their missions and also from radio amateur needs. And also we had a software update on Grafana that in the future we want to keep it up with the latest versions of Grafana and also again create new dashboards, involve more people, and also experiment with some Grafana dashboards, features, sorry. Then we go to operations. The last year, we have a kind of improvement, the auto-scheduler software, which is an external software to auto-scheduling the network stations. We schedule some special events like ARIS contacts or SSTV events. We also have scheduling observations for more than 15 satellite deployments. And we also support satellite teams that request our help for their missions, satellite missions. In the future, as I said before, we want to integrate this automated scheduling inside a SATNOX network. We are going to continue to support the special events and or scheduling requests by satellite teams. And also, we are going to continue to support new satellite deployments. Another thing in operations is the satellite identifications. I'll tell more in the next presentation about it. For now, we have identified more than 220 satellites and also sports a couple of misidentifications that happen some missions, some launches. Finally, we have the orbit determination and orbital data generation. We have created more than 300 TLE sets for the last year for several missions. We have generated TLEs before launches in some cases, and also we are in a level that we can generate TLE for satellites in the first hours after deployment, and also we generate TLEs that are accurate some hours before the re-entry of the satellite. And in this time, I want to thank the SATNOX community for all their contributions, which are very much for all the station owners that have joined the SATNOX network, people creating dashboards, decoders, support in our community forum, report bug fix issues, and also we have bug fixes and code development. And that's all for this presentation. If you have any questions.
We have 3 minutes for questions.
Thank you very much. Thank you very much. So, on what information exactly does the TLE determination depend? So, what information is required?
What we need for creating our own TLEs.
Yes, exactly. And also, how good it is in comparison to other databases?
Yeah, what we do is using the Doppler shift from our observations and also some external observations. I will talk about it in the next presentation in more detail. And we use this data to adjust the parameters of a TLE set. About the accuracy, in some cases we are much better than the published TLE sets. In other cases we are little less, little more around the accuracy. But we are trying to improve our processes, to improve our the results we get from observations, and all these, when they are going to be implemented, will give us much more accuracy in our calculations.
Thank you for the question. I will skip the introduction for the next talk because you already did. Yeah. Another question?
Okay.
Hi. So there are public components to the implementation, like the crowdsourced database, and I was wondering if there's a consideration in place in terms of security and robustness to avoid corruption, maybe from malicious agents and so forth.
In terms of the database and what data get in, we have a review process. So someone suggests a change and we review it. And we always, we have in suggestion a citation field that will link to the source that this information comes from. So we try to follow the official sites or information about, especially for transmitter frequencies and stuff, and until now it works good. But yeah, any suggestion to improve this process, it's more than welcome. In terms of network and how the stations work, and if someone can do malicious things, we follow a way to give the station owner the full control of the station. So the station owner is the one that defines the frequencies that can be used on his or her station, and also there is no access, remote access to the station. The station is actually asking things from network than the other way around.
Maybe a quick question.
Yeah.
Okay, thank you. You mentioned that you had to switch from NORAD ID to SatNOX ID.
Mm-hmm.
I want to know why they changed, because I know NORAD ID is more globally recognized, so why they changed?
In short, the problem with the NORAD ID is that satellites that are in orbit can have zero, one, or multiple possible NORAD IDs. So we wanted a way that when people send to us data, or when we say we want to observe a satellite, to know which one is it. So NORAD ID is not a good identifier. Yeah.
Also, I think that this is a use case that we saw. This is a use case that we saw yesterday. The NORAD ID is assigned after your launch. So if you want to do testing and post data in SatNOX, for example, beforehand in order to get ready or whatever, you don't have an assigned NORAD ID. So yeah, it's a big issue.
And we can discuss later more details about it. It's not fully complete right now across the SatNOX project, but we are getting there. So let's go to the next presentation.
Exactly, yeah. Presentation, Freddy. Thank you for the first presentation, Freddy.
So here I'm going to describe how we operate when we have a new launch that we want to do some observations, and mostly SSA, which is Space Situational Awareness, and Space Situational Traffic. I don't remember the SST right now. It's the European, let's say, abbreviation. So what we do, how we organize the SatNOX people when we have a new launch. So things are starting around usually 3 months before the launch, and it can continue to 3 weeks or more after the launch. And this part is gathering, this phase is for gathering information. Gathering information, like the tasks we perform during this phase is to gathering information about the satellite missions and the transmissions. We create the entries in DB with a suggestion process. We assign, for now, temporary NORAD IDs for compatibility reasons. We prepare and testing end-to-end support for satellite missions that came to us for integrate their missions into SatNOX. And also we create decoders and build dashboards for them. And also we usually open a forum, a thread in our forum in order to organizing and coordinating the information gathering and other processes. So what we gather when the satellite, when is the launch time, how many satellites are going to be deployed, when they are going deployed, also details about some basic details about the missions, like the country that launched the satellite, or some basic information like Oh, how we did that. Interesting. Okay, let me restart. We'll find it. Give me one moment. Okay, hopefully that will work. Cool. So fast to where we were. So other things that we gather is the transmission parameters, also decoding details, and also we try to find out the communications channels like social media sites or emails in order to contact, if necessary, the satellite teams. The next one, the sources that we usually use is the satellite teams. When they come to us, they give us the information, information from launch provider, from satellite mission online resources, some organizations especially for the frequencies, some online databases, and also other online resources like social media, forum sites, stuff. And also sometimes we use previous missions to speculate usually frequencies that probably the satellites will transmit to. The second phase, it's the pre-launch phase, one day before the launch. The tasks we do is to find or create our own preliminary orbital data. We prepare the SATNOX operator's working environment. We inform some observers that observe the whole spectrum for catching, receive more than one satellite at the same time. So we coordinate them and try to set which frequency ranges they are going to track. We also organize some third observers and also some reviewers for rating at the first days the observations we have in order to have a good picture of the satellites, the health of the satellites, and also ensure that SATNOX operators will be available the first hours after the launch. Then we have the scheduling observation phase, usually 1 hour before the launch, where we schedule observations for the first 12 hours usually after launch because we don't have accurate TLE yet. And then we also ensure that all the scheduling will be as fair as possible among all the launch satellites and the network stations. But this depends on the frequencies, on some frequency violations maybe. Yeah, it has different parameters. Then we have the launch phase, when we verify, usually from the streaming videos, the launch date time. We make sure that hasn't been changed. If it's changed, we update the orbital data, and if it's changed a lot, more than 1 minute difference in time, then we also reschedule the observations to have better results. If in case that the launch is postponed, then we remove the already scheduled observations. And also we keep updated the launch thread for third-party observers to know. Then we have the post-launch tracking phase, which starts after the launch, and it can take days or weeks. In this phase, we review the observation results as we're getting them, either from our network or we also are looking around for third-party observers. We generate orbital data if they are too off, or we have requests about generating them. We schedule, then we start, when we have more accurate data, we schedule observations for the next 48 hours. So every 2 days we schedule new observations. As I said, we watch communications channels to gather more information about the satellites, some missing informations, if they are received or not from the satellite teams or other observers. We also update the launch thread with all the latest info. And also if we have some news, because some satellites, they don't announce before the launch that they will be launched. So if needed, we create new entries in DB and update others. And then we are going to the identification phase, which can start from days to weeks usually, and can go to months, this process. So this is also known as TLE lottery, and it's separated in 2 sub-phases. The one phase is when the US Army published the objects that they have received with their radars. So they assign an NORAD ID, but the assignment is not final. So we wait until we have the second phase, where the NORAD IDs are assigned to the objects. And then we try to identify these objects and actually match the objects with the satellites that were launched. So the final identification is happening. It happens on the second phase when we have the full assignment. But we can start the identification process in the first phase with finding the first matches. Some tasks we are doing during this phase is first that all the objects that were launched are cataloged in the US Army list. If not, if we are missing some objects, then we wait before do the final identification, because sometimes one object could be several satellites, describe several satellites, or yeah, maybe we have a case of an object matching the satellite, but after some days it doesn't, because it wasn't published at all. How we do this identification, we compare the TLE from US Army with our network observations. We have tools for that. And we can first we find some candidates, and as the satellites separate, we can be more confident that this object is the satellite. In some cases, when we don't have data from the satellites, we don't have reception from the satellites, we randomly assign some TLEs to follow. And sometimes it's a semi-random, because we are based on size of the satellite, or we are based our decision on the deployment order, but this is still random. Then we also update our launch thread with all these details, so other people confirm our findings and also know if we have fully identified some objects. And also, when we are sure for the identifications, we form the satellite teams and also the US Army, especially when we spot misidentifications that sometimes happen. And then we have a phase after identification of satellites, or when the time after some months of observing them, if we don't have an identification, we stop actively tracking the satellites. Still, station owners can continue to track the satellites, so we suggest the satellite teams to give details about their missions and post updates in order to engage more the station owners and third-party observers to continue tracking their satellites. Some of them doing the special events we said before, like SSTV transmissions or enabling repeaters, especially for the radio amateurs. And then we, as operation teams for SATNOX, we are also available if if there is an emergency, like something is wrong with the transmission of the satellite, or it stopped, or it came back to life, or whatever. We are ready upon request to start again actively scheduling for specific satellites and actually start tracking again the satellite. Also, in some cases, we track the re-entries of satellites because during the re-entry, the orbit changes a lot and very fast. So we, in some missions and some after requests, we have tracked the re-entries of the satellites in minutes before re-entry, in some cases, like 8 minutes before, when the satellite sends like temperatures like 100 Celsius degrees, and yeah, like before burning. And more or less, this is how we track and satellite launches, and how we perform some SSA and SST operations in SATNOX network. Thank you. Any questions?
We have a question.
Yep.
Yeah, it's not so much a question, but kind of a observation, if you will. You said that in most cases the identification from SDS takes 1 to 2 days, but we found that especially in transporter launches with many satellites, it takes weeks, if at all. And yeah, I just wanted to say that the work that you do with helping identify the satellites based on these crowdsourced observations is extremely helpful, and I know of many satellite missions that wouldn't have been possible to operate without the work that you do here, so thank you.
Thank you. Yeah, it's very important, as you said, at least for the last 2 or 3 transporter mass launches, right-share launches, the official TLEs were published like around 3 weeks after the launch, where the satellites were very off from the preliminary TLEs. But usually around in 1 week, they publish not official and internal shared list, where you can use and start doing the matches. But usually this list is not public, so you need to find it either from satellite teams or from some collaborators with
Just one question. When people asked if you can track the satellite, is this competitive, or do you have to reject for lack of capacity or something? I have no idea.
It depends on a lot of parameters. For example, what frequency they use, what operations they want to do. But until now, I think we didn't have any issue. We tried to integrate it, the satellite mission, and usually it works. It works fine. The only note on this is if you have a mission and you want to integrate it into SATNOX, come as early as possible to us, in order to be able to verify that everything works fine and create all the dashboards, the decoders, all this stuff. And also, in some cases, we had some missions that came so early, like from their testing phase. So they used actually the dashboards and the decoders and all this stuff even before they actually give the satellites to be launched. And this was very helpful because in the launch time, everything was ready to help them. Manolis.
So who made the previous question?
The one before.
Yeah. So you mentioned about how critical is to identify your satellite early on, and with a traditional way, it takes even weeks. So let me ask you another question on this one. Are you willing to add a special beacon, let's say, if we say that there is a beacon that helps a lot to the identification phase, are you willing to do the extra effort in order to get it identified, let's say, in minutes and get the TLE?
Advertisement. It was an advertisement, yeah.
Maybe you're talking about SIDLOC. Yeah, I'm aware of this. And also at the TU Berlin, we are working on the Beacon project. And I've seen the prototype. It's like a little small unit that you put kind of on the outside of the satellite. I think that is very useful, in my opinion, to make the adoption even more widely applicable so that any satellite can use it. Ideally should be something that you can do software-based. But yeah, I think a self-contained unit that doesn't have any interface to the bus, self-powered and everything, I think that's something that I would use. And I think it's also easy to make the case that you will not lose your satellite, you will always know where it is, and from the very critical phase, you already have contact. Yeah. So go Beacon, go SIDLOC.
Just to give context to the rest that they don't know SIDLOC. SIDLOC actually is a device and a protocol at the same time that transmits some beacons at a certain frequency that we can receive and calculate the orbital data. As we do right now with SATNOX observations, this is for us is the next step because we will know before the launch the frequency. We do it in more performant way, and we will be able to get more accurate results. And also, yeah, we don't have and also it works independently from the rest of the satellite. So even if the satellite doesn't work, you still can spot it, identify it, and know which one is your satellite in order to keep your attempts to bring it back live or identify other objects on the same launch.
Are all SATNOX stations equally good for frequency accuracy for Doppler measurement? And is it taking into account in the orbit determination like some weighting based on the estimated or forecast frequency accuracy?
We haven't measured the frequency accuracy of stations. But I can say for sure that they are not always on spot. But we have found some methods that can mitigate these inaccuracies. And through the experimentation with satellites and launches, it works pretty well. There are plans maybe to equip somehow stations with like GPS clocks or other methods to synchronize and give us better results. But yeah, it's still an open discussion. But we want this. If we want more accurate orbital data, we need this. Thank you.
So the next speaker is Lefteris for me, or Eleftherios Kosmas for as known as, and we'll talk about Libre licensing for the final frontier. Lefteris is a colleague and fellow hacker, and also founder, one of the founders of the Libre Space Foundation, and he will try to make sense for the licenses that, I don't know, who understands them, yeah. Thank you, Lefteri.
Thank you. Let me first find my presentation. There's always Freddy around. Hey. Woohoo! So nice. Licensing. And when I say licensing, in terms of open source code, or hardware, or software, or data, it's actually the framework that creators place in such an artifact in order to be able to share. In most cases, yes. So in most cases, a lot of times I've seen licensing being an afterthought, not actually being part of a strategy of a project. It's sometimes what people do or how people are used to do stuff. But it creates a mission design parameter on any project. And it changes how you collaborate in many cases. There's the proprietary way, with vertical integration that can be slow, costly, but has a higher barrier to entry or whatever. And there's the open source way. And what we do believe that represents is the open source philosophy, first and foremost, but it has some practical results too. In terms of open source, there are kind of lots of licenses. You've heard of MIT, you've heard of GPL version 3, you name it. But the whole idea is that whatever you choose, it actually changes. It should depend on the goals of your project, on how you want to react, to how people react with your project, and what is suitable for your project. In most of our of LibreSpace cases, strong copyleft, like the GPL version 3 and AGPL, are what we choose. And for us, it's mostly because collaborative commons is our goal. And in many cases, that's what we try to actually do. There are cases that you're going to license your things in LGPL, which is a more broad license, if you like. And many people I know are going to use MIT. It is a choice. So, in terms of software, actually picking permissive license, like LGPL, MIT, it will maximize your adoption. In GPL version 3, it will build a protected and collaborative platform, if you like, and ensures that improvements are shared back to the community. And one of my favorites is the HPL, the license SatNux network uses. The HPL closes the software as a service loophole and guarantees modifications to the service are shared, which is really interesting. So in hardware, at LSF, we tend to choose the CERN open hardware license. I should have checked because actually you spell license, the CERN license with a C because it's British English, interesting. The CERN hardware license has 3 flavors: the permissive, the weak, and the strong, which can be a little bit complicated, but in the end, we mostly license our hardware using the strong license. And for us, it allows us to protect the full ecosystem, having it all everything under the copyleft license, if you like, a license that expects and allows for reciprocity in sharing. A strong open source license, in my opinion at least, allows for strong supply chain resilience, meaning that you can actually build a thing that's licensed under a strong license. And there are examples of entities other than LSF that have built SatNux comms. And yes, they do collaborate with us in many cases, but they prefer to build their own, which is cool. For data, we tend to use Creative Commons licensing. In most scientific work, the current standard is CC0, that's not an O, which is actually the public domain license. But we do prefer to use Seralike, because we do prefer for people to actually share the data that's the byproduct of the data we shared. One such use is SatNuxDB, which actually shares this data all over the place. A very important thing, in my humble opinion, is also how you accept contributions. And in most cases, especially in corporate environments, even open source corporate environments, which do exist, a formal legal document is expected. In our case, as is the Linux Foundation's case, and in many other cases, what we do is actually expect a DCO, Developer Certificate of Origin, which you actually a per commit statement signed off by me, which allows us to at least certify that they submit the code they own. And sometimes what you end up having as an issue is licensing compatibility, meaning that you can't actually easily mix and match licenses, like sharing GPL version 2 with Apache 2. It can be a little bit complicated. In many cases, a solution in this is to use software composition analysis in your pipeline. It's really interesting. We're going to talk about it a little bit further. Next is failing to license. I don't put a license there, but it's in GitHub, so it should be open source. It's not the case. You have to put a license. If you don't, it's considered to be a copyrighted work. And I think that I'm not really comfortable with is using your own custom licensing, which can be really problematic because nobody will adopt it, and it's going to be a legal trap. So yeah. I'm talking about how you actually can use software composition analysis. And what you actually do is include these tools in your continuous development pipelines in GitLab and GitHub, and which may allow you to better control the licensing, which can be important. And a few days ago, we had a really interesting chat at the Liberspace channel with a fellow here from TU Berlin. And we were discussing about export controls and how you manage that. And first and foremost, a standard license is really useful here because in most cases, you have something already done. It's not a legal black hole that you don't know what you're trying to do. Both the USA and the EU implement export controls on space technologies, and other jurisdictions too. There are EU regulations, but that may change depending on your jurisdiction, which can be a little bit funny. And the United States paradigm, which is a little bit complex because you can talk to your colleague that might not be a US person, and then what you did is actually exporting technologies, which is a little bit weird, in my humble opinion at least. But that's the rule of law in the United States. But the rule of law actually recognizes that stuff that are accessible to people are actually part of the public domain, not the public domain we are used to actually think about, but the public domain in a more non-legal way, meaning that if it's accessible to someone, then it's not restricted. So there was a legal process from the Open Research Institute that actually confirmed that. And in the European Union, there are some regulations which identify, that's my note to be in here. So there are some regulations which identify what are the legal frameworks of what you can share. And the last regulation in 2024 actually included a lot of space technologies. But still, the public domain exception is a thing, but it's not tested yet. Are we going to test it? I don't know. We will see. So, in simple terms, if you would like a checklist, because I know people like checklists in space, you have to set your goals, what you are trying to do. Are you trying to build an ecosystem? Are you trying to build a tool that you wanted adopted? Then you have to have cohesion, meaning that your hardware licenses and your software licenses and your data licenses must be compatible and ideally serve the same goals. For community engagement, I believe that TCO is the way to go, in my humble opinion. For compliance, is using SCA tools and being radically open allows you to actually use the public domain exceptions as a strategic advance, and having a vision that don't actually include using space for nefarious users is actually a good idea, in my humble opinion. I have to thank my colleague Nicoletta for long talks about licensing and long questions. That's all from me. I'm looking forward to hear your questions or comments or anything.
You spoke about licensing, and I think that licensing goes hand in hand with a software bill of materials, because that way you can track what you're adding in. Is there a formal recommendation about how to structure that SBOM along with licensing tracking by Libre Foundation or in space in general?
We don't actually do follow such a process, not to my knowledge at least. But in many cases, the idea is to actually use tools like Trivi, for example, that would allow you to actually have a basic understanding of your software, which in many cases can be problematic. I mean, you might be a software developer, you've seen people having dependencies that didn't know they had. So yeah, that can be a case. But tools like Trivi can be really helpful, in my humble opinion, at least.
Hey, thanks for the talk. It was really interesting. Just walked in and came through live stream to here as well. So in your talk, you essentially usually talked about licensing of implementations and picking the right license and so on and so forth. Difficult thing, yes. Ran into that many, many times. The rest was essentially more about IP protection. But that's more or less an unresolved issue. As soon as you put source code out there in the world, your IP is exposed. Sometimes very nice and friendly big corporations look kindly at open source developers and tell them, hey, here's a tiny bit of money, keep doing that. In the background, there's an entire team of people just cloning your stuff. They absolutely don't care about your implementation. They can't use it anyway. There are standards that directly ban them from doing that due to quality assurance reasons. What about IP protection in general?
Okay, that's a nice question. And in my humble opinion, you've seen in many cases in the past that proprietary software have been found of including open source code without proper licensing, without any licensing actually. And I know that the standard in many cases is to actually not seek remedies and actually just expect them to release the code, etc., etc. We all know how it goes. In my humble opinion, and that's a personal opinion of mine only, I believe that we as users and foundations that are actually using open source and respect the open source idea should actively seek remedies in such cases. But I understand that in many cases you can't actually find out, and that's an issue. And in some cases, by design, it's too difficult to not find out. And in many cases, you're going to actually have people violating your IP. You know that. But let's be honest. Proprietary software has that issue as well. So I know that my answer might not be a real answer to what you're asking, but I do believe that, that there is a sentiment in the open source community, not only LibreSpace Foundation, in several communities, that a more active way of seeking remedies for IP theft, actually, should be implemented.
Thanks. So it's a counterpoint mainly that you cannot do actual open source and protect your IP in a meaningful way because, as the code goes, as the saying goes, locks protect you from honest people. So if someone is dishonest, there's nothing you can do about it. Fight in the court of law and hope you win. But at the end of the day, you're either committed to the idea of, offering something to the world and doing open source, or you're not and you're trying to patent things and hope you monetize it successfully.
I mean, something like suing a mega corporation and trying to win a lawsuit there is completely ridiculous. They'll simply hire a team of lawyers and you'll spend all your money for the next 20 years. If you're a startup, that will just bankrupt you. I mean, what happened in our case was that we simply stopped doing open source, which is very sad. I mean, when you go from getting paid by GNU to not doing it anymore at all, because people at conferences tell you, yay, great, thank you very much for publishing that, and now it's flying on our LEO Earth observation constellation. It's, the credit that you get doesn't really help, though. So that's why, I just wanted to bring that topic up, and I'm actually curious if anyone found any way to work with this.
So I will also maybe give my personal, perhaps slightly controversial opinion here. So let's say that you produce a very useful piece of software and you license it with GPL version 3 because you believe that accepting contributions from people that use your software is the way to go. And now the question is, how do you prevent companies from stealing this IP, right? So one possible solution, and again, this might be controversial here, but is this dual licensing approach. So you say, okay, you can use my code with the GPL version 3 license, and then you must make your derivative work also licensed with the same license. But in the real world, we know that many entities will simply not do this, and they will just say, okay, thanks for your code, I'll use it in this way. But if you do offer a way to say, okay, I'll give you 5,000 euros to get a different license for your code, and then you can use this money to further develop the software, then it might be like a, some kind of compromise. This is my opinion.
Totally agree. Main issue is that only protects your implementation. Again, like your Airbus, your Thales, your Boeing, your Northrop Grumman, your CSA doesn't care about your source code. They don't want it. They can't use it. What they're going for is reading the source code, understanding your concept, and then re-implementing that, just without you.
I think that's fine, actually.
Let's continue the discussion during the break. Sorry for interrupting.
I'm not at your availability during the break. Don't hesitate to discuss, and there are also break rooms available if you would like to use them to actually have a talk, totally informal, about our issues and how we should remedy or how we should, as organizations, protect ourselves from such conditions. I would be happy to actually have a chat about that.
Ooh, coffee break, people.
So, should we start the next session? Are we okay? So we have a change in schedule. The next two presenters are not here, so we'll have Manolis here doing a presentation about SeedLock, something he already talked about on the comments, and afterwards the next two presentations will become after Manolis. And we have 2 spots for presentations, so if you like to give a lightning talk or like present something, like be free to do it after the lunch break. So here is Manoglis, and he will talk about SeedLock, a satellite identification and localization protocol we developed together with ESA. Like. Thank you. Here's your time.
Good morning. I'm Manolis from Libre Space Foundation. And I will present you the SeedLock system and how it works, what its goal, and our latest achievement, which was the in-flight demonstration with Ariane 6. Test? Yeah, okay. Sorry about that. Okay, so what is SeedLock and what it is trying to achieve? Maybe all of you are aware of the main issue that was discussed a few minutes ago, which is, of course, that's it. Okay. It is satellite identification. Okay, it's a big issue, especially for us, for our community, which targets small satellites with a limited budget. Okay, there is, as you mentioned, there is TLEs available, but all of you know that they are free, but not Libre. So most of them are provided by entities like the US military, the French military, and of course they have limitations. One of the major limitations right now is that they don't give public data for tracking of objects less than 10 centimeters. Is that a problem for you? For the CubeSat domain, maybe not, but for the pocket cubes that are rising, it is. And of course, you mentioned that identification may take, especially on transporter, on busy transporter launches, may take weeks. So how the classic model right now is to use huge radars like this one. Oh, sorry, yeah, like this one. That are targeting the sky, and when those objects are above the field of view of this radar, they get a signal back and they try to identify it. What we want to do with SIDLOC is to make the space object active and using some special signal characteristics to make the identification easier. So the idea is that you place a very small beacon with quite limited transmission power. This is quite crucial. I will discuss it about it later. And as you launch your space application, CubeSat, PocketCube, or Microsat, or whatever, when it is getting deployed after the separation, it starts to transmit some special kind of beacons. Then, using a crowdsourced network or your network or whatever, you can get those signals. And with post-processing and analysis, you can pretty reliably estimate the trajectory, and therefore then, with some extra processing, produce TLAs that you can use to track your satellite and communicate with it. So the key characteristics of and the goals of SIDLOC is to be quite low in power, for two main reasons. One is for not disrupting a lot the well-being of the mothercraft, either it is a CubeSat or a PocketCube or a Microsat. And the second one is for regulations. Okay, if the transmission beacons was quite high in power, it is very, very difficult to get licensing for a specific service that multiple entities may use. The second key point is that SIDLOC is quite low in terms of cost and has zero maintenance. So it is very cheap to produce it on your own or buy it if at some point we provide it as a product, let's say. And you bolt this into your superstructure, and that's it. You don't care, you don't have any kind of other things to do. So this helps a lot in the integration of your system. And if it is a small size, maybe you can find some spaces to bolt it and don't care about it at all. Once you place it on your spacecraft, it is completely autonomous. It can piggyback some kind of information, we'll see it later. But the idea is that once deployed in space, your satellite the SIDLOC beacon starts to transmit, so you can get an identification, and that's it. You don't have to do any kind of extra integration effort from your OBC or whatever. And of course, you can take advantage of the SATNOX network, because SIDLOC operates on the UHF frequencies, and SATNOX right now, the majority of SATNOX stations right now are operating on the UHF, and get the results and the TLE estimations directly after your launch. So regarding the transmission scheme, it is using the UHF frequencies. These are specially allocated frequencies. We paid a lot of effort with, together with ESA to secure those frequencies, and right now there is a filing for SIDLOC, for a SIDLOC network on those specific frequencies. The bandwidth, the occupied bandwidth is around 1 megahertz, and use direct spectrum technology over BPSK. It is quite similar to the GPS with some kind of modifications. So it uses a gold sequence of 2K long bits. Gold sequences have some very nice cross-correlation properties that we take into advantage in order to be able to decode on the ground the signal. And each of these gold sequences, for each bit symbol, is repeated 10 times which results in an effective bit rate of around 50 bits per second. So the data rate is ridiculously low, but it is enough to carry some basic information, and also it is quite enough to estimate accurately the orbit. The TX power, as I said before, it's quite low, and at this time it is 25 dBm. We believe that we can somehow go even lower, but as we are in the development phase, it starts at 25. So how it works, the TX procedure is ridiculously simple. Here is all what you need to know about how it works. So you have a clock operating, as I said before, at around 1 megabit, and you spread in time your bit information, as I saw in this schematic, by the gold sequence length multiplied 10 times. So the resulting bit stream that operates at 1 megabit is modulated with BPSK and sent over the air. So quite simple, very easy to implement with just basic DSP. You can even implement it yourself. This is the equivalent TX flow graph that we are using for testing in GNU Radio. So maybe you can, even now, you can get the code, the GNU Radio module, and start transmitting SIDLOC beacons in order to experiment or whatever you may need. On the other hand, reception is not easy. This is a very well-known issue of the DSSS. So, and there is a game and a trade-off between sensitivity versus computational cost. Imagine that if you want, theoretically you can even decode the SIDLOC signal in minus 30 dB of SNR. It's ridiculously low SNR. It's negative because it's below the noise floor. But you need an i7 and extremely fast clock frequency in order to achieve the real-time limit. So there are trade-offs, and of course, as you decrease the transmission, the computational power required, you reduce the sensitivity. There are two major different algorithms that you can use to decode those kind of signals. It's the autocorrelation one and the cross correlation. The autocorrelation is quite easy, but lacks in terms of sensitivity performance. And the cross correlation one, it's let's say more sensitive, but needs a lot of extra effort in order to get correctly the bits. In the cross correlation domain, there are also two different approaches, the coherent and no-coherent. Currently, we use the coherent, but we have also got some good results with the non-coherent, which is a bit lighter in terms of CPU requirements. So SIDLOC defines three different beacon types. Recall that the bit rate is quite low. The effective bit rate is quite low. It's 50 bits per second. Sorry. So having more information to transmit means more power. And in a system that it's tiny, it's like this. So having that power, it's not easy. So you want to keep the things as small as possible, and in order to adapt better in different missions and requirements of those missions, we have identified three different beacon types. The minimal one, which carries the necessary SIDLOC information so the receiver can decode the signal, and a unique satellite ID that we discussed previously. Could be the SatNOX satellite ID or whatever you may think about. The full one has some extra fields that may even more assist the ground station procedure to compute a more accurate TLE. That information is, of course, the date time and the location that may be available on the satellite through a GNSS subsystem, for example. And the integrated has two extra fields that are optional that you may piggyback extra information from your OBC or for any subsystem that you may like. A very common case, it's that the OBC is, let's say, operational. It's on. Just a heartbeat from the OBC, or that the antennas of the satellites are deployed. Think anything about it. SIDLOC will carry it. We have dedicated fields about that. And this one is the full analysis of all those fields that we discussed previously. It just it contains the information that mostly from the GNSS and what is and the coordinate system that it may use, and of course a CRC for the ground station to be sure that the SIDLOC beacon is correct. So we have already built some SIDLOC beacons, and we have a reference design about them, for them. Currently, we use a very low power microcontroller. It's an STM32L4. A transceiver that can operate in IQ mode, like a small SDR, which is the 8086, and a small FPGA for doing the DSP, which have been selected the ECP5 from Lattice. This is the reference design as it stands right now. But again, this is just an example of implementation. We would like to define the protocol, not the implementation. Okay, so this is our reference design. And we had the chance to fly this with the first flight of Ariane 6. So our system was selected for one of the payloads on board the Ariane 6. Unfortunately, we decided not to deploy it, but stay attached with the second stage. I say unfortunately because we planned that after the re-entry burn, everything will be destroyed in atmosphere. Unfortunately, Ariane 6 didn't manage to re-entry, so it's still orbiting around the Earth. But having that in mind, we didn't place any kind of solar panels. So the battery after 2 orbits was dead, and yeah, we had a huge opportunity to still be there and transmitting, but no. So this is the SIDLOC beacon that flew with Ariane. It's like a pocket tube. It's 5 by 5 by 5. And it has, as you see, a ridiculously deep sub-9 connector comparing to the other spacecraft, because it was the smallest connector that Ariane accepted. So yeah, it was ridiculous comparing to the other spacecraft. So yeah, this is the SIDLOC with a protective case on board the second stage. This is the integration facility in Kourou. An amazing experience working there with Ariane. This is the reference ground station for SIDLOC. It's quite simple with Omni antenna. This is the approach that we envision. A very simple setup. A Raspberry Pi decoding, a GPS DO assisted USRP, and a low noise amplifier, and just Omni antenna. And the experiment went amazing. On the first pass, we were able to retrieve the SIDLOC transmissions. This is the result of the analysis, and the x-axis is the time, and the y-axis is the frequency offset, and the color intensity specifies the confidence level, how the decoder, how sure the decoder is that this is a signal estimation. Okay, so as you can see, it's, you can clearly observe the characteristic Doppler curve. Okay, and after that, with a bit of filtering and curve fitting, you can estimate the TLE. On the line, on the solid line, there is it is the estimation from space, or not the estimation, the spacecraft reported trajectory of Ariane through the TLE provided by spacecraft, and the dots are the estimation from SIDLOG. So you can see that we have a quite nice fitting, and at the end, we managed to produce our TLEs, which are almost perfectly matched with those from spacecraft. So that's all from SIDLOG. We are very, very proud that anything developed on this project was used only open tools, from the hardware with KiCad to the software with GNU Radio, Zephyr, from the mechanical with FreeCAD. And also, and last but not least, for the FPGA with Yossi's, NextP and ARC, and Project Rails. So thanks all. If you need any kind of more information, you can find them on our GitLab projects and on a dedicated Matrix channel that we have. Thank you.
We have time for one question or two.
Thank you. Sorry if I missed it, but I understand SIDLOG is a completely independent module, but you also have some information from the OBC in some of the variants.
It's optional.
Yeah. So how does that work? How do you transmit data from the OBC to a module that is completely separated?
We have a CAN interface, so if you want to piggyback extra information, you have to connect to a CAN bus. But again, this is just a reference implementation. It doesn't mean that it should be CAN. Maybe you need something else, or you decide to implement something else. We want to provide the protocol, not the implementation. Okay.
Maybe it would be interesting if you could do this data transfer wirelessly, so there really are no physical connections to the satellite. Just an idea.
Have you considered morphing all of this more into something like an IP core that you can just give someone to put on their FPGA?
On the FPGA?
Yeah. Have you considered to just turn that into an IP core that you can give or license, for example, to an SDR supplier, some transceivers vendor, like so say give it to Clyde Space, Gamma Space, someone like that to integrate it into their products?
The DSP is performed on the FPGA already. So the beacon has an IP core based on the ACP5 and LiteX project. Okay, so it's not like an IP core. It's the LiteX project that implements the DSP. Okay, and then the LiteX produces the IQ, and we use a small SDR that is based on the 8086 transceiver already. So it is on the FPGA, yes, already. Yeah, you can do that. Yeah. We even have the GNU Radio flow graph, so you can you can use a USRP, for example, and transmit it.
Okay, but that would be up to someone else, right?
Yeah. Thank you.
So the next presenter is Henk. Henk is an employee at WAG Future Lab for 25 years and global instructor at the FAB Academy. And he will talk about FabSat, prototyping open satellite infrastructure across global Fab Lab network. So Henk.
Okay, yeah, I'm Henk, working at WAG Future Lab in Amsterdam. We are based in Amsterdam, Netherlands. And first, first about me, making the planet since 1965. I'm self-educated. I always worked in social and activist settings. Did my analog to digital conversion in the late 90s, late 80s. Becoming a media activist, network engineer, and then started as network engineer in 2000 at WAG. Then called Society for All the New Media. And since 2018, I'm hacking in the Fab Lab and in the Fab Academy. And that's my contact address. So, oh, that's the wrong key. So this is a 500 years old building. In the Society for All the New Media is located on the second and the third floor. It's in the city center of Amsterdam. And it is an institute, it's let's say an NGO, researching art, science and technology. So we work with artists, with scientists, with makers and hackers to make a better society. Let's say that. Okay. So as I said, I work in the Fab Lab. This is the Fab Charter. For the people that don't know what a Fab Lab is, so Fab Lab is a space where we make, share and learn. That's Fab Lab in 3 words. It's a space with machines, but more important, it's a space where people can meet and work together on ideas with the use of and to make do projects and prototype with machines that are in the space. So it's a Fab Lab is a global network of local labs, and it provides access for individuals to tools that you can normally not get your hands on, like, I will tell later. And what's more important is that it is a global network. So there are a lot of labs that work together and they all share the same tools and equipment. And also the inventory, I'll come to that later. So what's important for this community, for the labs, is that we share everything. So once a person designs something, make new hardware, software, whatever, that it's documented and publicly shared, so that the other labs also can build on the prototypes that were made. And what's really important is that we it's a learning facility. So people from all kinds of backgrounds can enter the Fab Lab, and they can learn from each other, share information, work together, and build projects, build a curriculum, and learn and have fun, and also to realize projects. So it's like open content. So we share all information. The best viewed is on the documentation of the students of the Fab Academy. They have to document everything they do. They have to publish all designs and code they use. And similar for the things they make. It's all published on our GitLab server. So at the moment we have around 2,500 labs on all continents. But they're quite diverse. Some are focused on STEAM education. Some labs are in public libraries to reach also people in neighborhoods. Some are based in universities to help the students to make stuff. Neighborhoods, some are more focused on art. And there are some groups that especially take care of health. So they design, for instance, prostheses that you can make locally in any Fab Lab. We have 3 main academies globally. One is the Fab Academy. It are 70 nodes. As you can see, also it's on any continent. There's at least one node. And yearly we have around 300 students. You have the Fabric Academy, also called the Textile Academy, more focused on sustainability, on new materials, and we're going to start at the end of this year with the Fab Futures, which is more focused on vocational training. The first Fab Future module will be on data science. The second one on chip design. Then there will be a module on cybersecurity, a module on machine learning, and so on. So we don't know where it will develop, but it's a way to expand the academy. So what we share is the machines. So the subtitle of the Fab Academy is the academy to make almost anything. And to make almost anything, we have a set of 5 machines that every Fab Lab has. So it's a laser cutter, a 3D printer, a big CNC milling machine, a small milling machine to make PCBs, and a final cutter. And with a final cutter, it looks like the least usable machine, but you can do amazing stuff with final cutters. For instance, make flexible PCBs and so on. The other thing what we share is the inventory. So this is a part of the electronics inventory with different processors that we use, logic analyzers, cables, breadboards, and so on. So we have a quite complete inventory where we can make, that we use to make almost anything. And it's every fab lab more or less has this inventory. So it's quite easy to multiply or to take designs from others and modify them, and so and Micha, my colleague, will speak after me, and we came up with this idea of FabSat. So a satellite that can be designed and built using the resources that are available in any fab lab worldwide. And we want this to explore how space-based systems can be democratized through open source and locally producible designs. And so that's the goal. So, 2 years ago, we have, no, let's say it differently. So we have a yearly conference somewhere in the world, mostly in July, August, where all the graduates from the Fab Academy and the Fabric Academy come and get their graduation, and where also many people from other fab labs come and gather and work for 1 week on new stuff, share information, but also have fun. So 2 years ago in Mexico, I did an antenna building workshop for Satnok's ground station. And we, in 2 days, so we were able to make a working satellite ground station. It was fun. And then this was a couple of months ago at Fab 25, where with the help of Georges and Freddy, we did an antenna building workshop. And how many antennas did we build? Couple, 5 or 6, yeah. So it was fun. And we had, I think we had about 20 people that joined. They joined, and they all, they liked it. So we had great fun 2 days. Yeah, what's next? So next, this FabSat. So we are here to see where to start, because we don't know where to start. So in the coming days, so I hope to get an idea where we could start if it's possible. I think it's possible. So yeah. Okay, questions?
Hello. Is there any Fab Lab here in Greece? And if not, which is the closest Fab Lab?
I don't know. Freddy, do you know? There are some Fab Labs, I think, in Greece. I know there's There's no Fab Lab that is part of this Fab Academy program. And the closest Fab Lab that does a Fab Academy program is probably in Turkey or Italy. In Italy, there are several labs. That, in Venice?
Is there any Fab Lab in Venice, close to Venice?
Yeah, I think there is. In Italy, there are a lot of Fab Labs.
Not okay. That's thank you.
Okay.
So one question I got is, what's the requirement to open a Fab Lab in your local country? Do you have to have a bunch of equipment at the beginning, or can you start if you have a room and maybe a PCB router or something like that?
Yeah, to call it a Fab Lab, you need at least more than one machine. But we had this problem in the beginning. So when we started this Fab Lab network, and in the beginning, I saw people signed up because they had a 3D printer at home. So the idea behind the Fab Lab is that you have the tools where you can make almost anything. So you also need equipment not only to make electronics, but also equipment to make casing or whatever.
If I may follow up on that, like with funding and budgets for that, how do you organize it in that way? Like, do people just pay for what they use, or do you get something external to fund it?
It all depends on the Fab Lab. Okay. But so in general, the business model behind the Fab Lab completely sucks.
Okay.
Now imagine, so you need a space, but a bigger space, where you have expensive machines that can't produce. So you can use the machines to make prototypes, but you can't produce. So it's, business-wise, it's a quite stupid model. But that's why many Fab Labs are in institutions, in universities, and the Fab Lab I like most from this. So it's a friend of mine. He started a Fab Lab 20 years ago, looking for ways to make it sustainable. And after trying everything out, after 10 years, he made a daycare facility for people with autism. And so that's a really sustainable Fab Lab.
Thank you.
Any other question? Okay, let's thank. And now we're going to do break for lunch.
Break.
Oh, not lunch, lunch. And we will be back at So let's do the break now and return back to.
So, should we start? People on the back. Should we start? No, they're looking to posters, but should we? Should we start? Okay, okay. So the next talk is yeah. So the next talk is is a continuation from the previous one before the lunch. So Micha, he will talk about open planetary infrastructure, and Micha is a lead in Space Lab in VAG, and he develops international collaborations at the intersection of art and science. And yeah, the floor is yours, yeah?
Thank you. Whoops. So very quickly, this presentation is not going to be so much how things function, but maybe why they are as they are. Also because I'm coming more from arts and culture, even though in the space context for the last 20 years. And my background is in, let's say, theater performance in a parabolic flight, theater performance in a cosmonaut training centers, art that relates to outer space from early 20th century. So like it's a story of like 100 years of art that relates to outer space. So there is a thing that is art, space culture, and space philosophy. So that's a bit of my background. However, at VAG, as Henk mentioned before, we research technologies more from societal perspectives and from cultural perspectives. And in this sense, I'm going to talk about, let's move on if we manage. Yeah. So for last 3 years in our community, so it's like community of artists and researchers from culture and humanities for outer space, we researched a very simple phenomena. We call it people understand our planet in very different ways. So we used to hear like there's no planet B. There's only one planet. However, we don't agree what is this planet A. And our philosophers literally say, you and I don't live on the same planet because we understand it in such a different ways. Some see it as a resource of, resources for the industry. Others see it as something that needs to be taken care of. So literally, different cultures, different people don't agree what we're even looking at. And one of our researchers came up with the analogy of the image that is usually used to portray how America was found. So this is the image that most of us, especially in Europe, in the Western society, that's how we imagine that the Europeans came to the Caribbean and found a new world. However, if you know the history of this image, it was done by some German artists that were never in America. They never saw indigenous people, and they were not at the place where the event happened. So the same analogy is for this image here that we all take for granted. Everybody thinks that this is how our planet looks like. However, when you know that there's specific knowledge behind it, specific technologies behind it, it makes sense. But other people work with different imaginaries, different technologies and different knowledges, and for their worldview, this doesn't make sense. So what we studied for like 3 years with more than 100 artists, researchers, what we do is more collaborative research. We organize workshops, symposia, sessions, and we research these kind of questions in a collaborative way. So we came up with what is called Modern Planet Atlas. Here you can download it. It was published like a month ago. And we mapped out different knowledges, different worldviews, different technological stacks, different value systems that drive this notion, what is the planet? And that's why we describe it more than a planet, because there's more than one understanding of our planet and how these notions are produced through technologies. And I'm presenting this here especially because there's a special value of open source approach, of community approach in making of technologies that portray our planet. First level that we explored is what we call comparative planetology. So when I use words like land, place, territory, borders, globe, Earth system, Gaia, planetary, planet, Anthropocene. So we use all these words, but all these words project, imagine completely different worlds, completely different concepts. And really, it really matters which word, which concept you use for the shaping of the planet. So when you make new policies, new technologies, new educational programs, it really matters which one you take as a point of departure. For our case here, for this workshop, I would focus on the concept that we call Earth-Space Society, because everything that you and we do in what we call outer space is made here on the Earth. It's made through the way we are organized, and we are organized in different ways. At the same time, things that we do in outer space influence our society here. So when there's a huge militarization of space sector, huge industrialization of space sector, all these approaches are influencing the way our society is organized and the way we understand our environment. So the way we organize and the way this workshop here is organized is completely different from a usual space industry event, for example. So it really matters how you organize and what kind of technologies do you make for outer space, because they shape our societies in different ways. So open source approach, Libre approach is essential for more community-driven understanding of the planet and our societies. And these technologies are shaping our societies in different ways. The second layer that we explored are what we call knowledge cultures. So you are familiar with science, technologies, business, economy. So these are the knowledges that are driving the space sector. However, what we call open source, open design, citizen sensing, activism, it's closer to more societal approaches. And they produce different kind of knowledge that is shaping different kind of understanding of our planet. We also have arts, from fictioning, media studies, environmental humanities, ethics, artistic research. Again, they're producing more critical understanding of the knowledges, of technologies, of the way we are organized. So all of a sudden, so we mapped out all these different, we call them knowledge cultures. And we explored how they shape our environment and our technologies in different ways. And I would point out mainly to two of them. One is critical making or critical engineering, where it's not enough to have to be a critical thinker, like questioning authorities, questioning systems of licensing. You have to make it to be actually critical. You have to have your licensing models and you have to use them to kind of a challenge and to have kind of a different way people organize for making new technologies. So that's one of them that and it's really shared way of knowing from the people from, let's say, arts, humanities, technologies. Also our Fab Lab is a core of, let's say, critical making approach. Another one is pluriverse. So you are familiar with the universal or the universe. That's the universe and universal approach is driven by science. They say there's only one understanding of space, of the universe. But at the same time, we know that there are older knowledges that also tend to explain everything. So we have, let's say, Ubuntu, Jain, Ben-Gvir, so different culture backgrounds. They also explain the whole universe and the planet and the way life functions in completely or quite different ways. And they also have universal approaches. So what we see that there are different universal knowledges that coexist at the same time, which is important because they also make their own technologies, they also shape environment in their own way, they also shape society in their own way. So this coexistence is important mainly to get over how some things are taken for granted while they shouldn't be, which is specific for more Western knowledges, but not for most of the others. The second one is that we understand that media technologies are shaping the environment. Also, we know media technologies are shaping our society. And what we do understand in our concept here that satellites are media technologies. They produce data, they produce the way we imagine things. So that's why we study all these technologies, so satellite technologies as media technologies in the context of how they shape, as I said, environment and society. And I would just point to one case here. It's a project from the 90s. It's called TerraVision. Also because you were talking before about licensing and how it works or how it doesn't work. So this was the first project by German artists in Berlin on virtual world. So they made the first satellite images, put them on the globe as an interface so that you could experience how the whole planet looks like. This project was stolen by Google and made into Google Earth and Google Map. So today, on your phones, you have Google Maps, Apple Maps, all these applications. That's where they come from the project that was literally stolen from the artist. But it's not a sad story. Because a few years ago, Netflix produced a film about the court case and the conflict between both of them. And even though the artist lost the court case, they got a film on Netflix and told the story how Google stole the code. So you can overcome, let's say, stealing of the knowledge, stealing of the code. Even the title of the film is The Billion-Dollar Code. Through the cultural field, you can establish values. You can tell stories that go beyond just business, technologies, and property, and these kind of things. Oh, wow. Oh, wow. So, now you have to imagine. Obviously, the thing didn't download properly. It's fine. The last layer that we explored is what we call how planet matters. And you're all familiar with facts. So science is producing facts, data, and this is kind of a foundation for what we agree about. And most of the facts are produced for the sake of, let's say, using the environment. So satellites are used for agriculture, so that fields can be properly managed. And it's really, again, it's resource-based understanding of our environment. On the other side, we have, let's say, a lot of pollution. A lot of pollution is, again, result of intensive industrialization, intensive agriculture, and these kind of things. So we have communities of people using space technologies not to use the environment, but to protect themselves from, let's say, intensive use of the environment or excessive industrialization. At the same time, for example, we have this counter use of space data, for example, now in Gaza, where satellite technologies are used for, on one side, for the genocide, while the Palestinian Space Institute is using the same data to track and document the genocide, for example. We have space organizations that work, let's say, Space Pride, that work on the question of, say, diversity in the space sector, because it matters. Who is, not just gender balance, for example, but also what kind of perspectives, what kind of questions are allowed in the space sector to be kind of addressed and researched. So we see that there are values behind everything that we do. Technologies are not neutral, knowledge is not neutral, and the values behind, that's something that we mapped out. And I think there's everything empty here. Yeah, it's fine. I mean, I had a few more cases of artworks that show how we open infrastructures. So there's one artwork by one Serbian artist, Vladan Jolar, and American researcher, Kate Crawford. They mapped out all computational technologies from last 500 years. And they made like 25 meters long, very detailed map of all these technologies. So you can imagine this wall full of very small, it's a huge infographic. So they mapped out all the computational technologies used by, let's say, states or the power, imperias and these kind of structures. So it's important to kind of open, to get to the public understanding how, not just how AI works, but where it comes from. What's the legacy of AI, of satellite technologies, and these kind of things. There's a project, it's called the Solar Protocol. Again, more critical makers, they made a solar-powered servers. So it's a network of, I mean, it's a small project. It's like 10 to 15 servers around the Earth, all powered by the solar panels. And only those servers that are powered by the sun are running. So you have a DNS service that kind of that connects you only to the servers that are kind of powered by solar panels. So it's again a critical thinking of what powers our servers, what powers our, let's say, internet in a very critical way, kind of showing that you can connect, you can power our daily internet in a completely different way. So my main message here is open source satellites are not just a good technology, something that is, let's say, works well. Open source technologies shape our, let's say, the way we organize in a completely different way than proprietary space technologies or big tech space genre, because we share ideas in completely different ways. Oh yeah, so I'll just quickly show you this work so that you get a bit of an idea how they look like. So this is like really detailed, 25 meters long print. The Solar Protocol, it's hardware, software, like SatNox, but for solar-powered servers, and you can connect only to those that are that have energy. And then also an open weather community, which is close to SatNox, but their goal is mainly into building the community around understanding the weather. So it's not so much technology-driven, it's more driven by how do we organize and how understanding weather is important for us and how we function. And for me, your challenge on these technologies, so open source technologies, community-driven technologies, challenge mainly in this public context. So what is public sector? Who define, I mean, public spectrum? Who defines it? Who is involved, who is not involved? That's our main challenge here. And I mean, that's why also the FabSat project that we're launching now, and yeah, we're looking for your input, because for us it's important how we organize in developing next steps in the space technologies. Thank you, and if you have any questions, let me know.
Hello, thank you for the presentation. If I understood you correctly, you're essentially discussing not one isolated aspect of open community and even technology and science, but how that comes together to form something bigger than the individual parts? And if so, do you also take inspiration from philosophy and let's say schools of philosophy like epistemology and you know, how something can move from being science to being art while retaining the aspects of science?
Yes, absolutely. So, I mean, I didn't show part of our program at Bach. It's called START. It's part of this European Initiative on Science, Technologies and Arts. It's a program for the last 10 years running with like millions of investment into a number of residencies, collaborations between scientists, technologists, artists, researchers, policymakers, into how can we collaborate and how different ways of collaboration form new way of understanding, new way of innovation. So it's research-driven and innovation-driven. And the outcomes are not artworks, I mean, sometimes, but mainly it's new knowledge for new way of innovation. And we often work also with industry that, I mean, robotics, AI, water technologies, to kind of see how different type of knowledges contribute to new kind of solutions. So definitely it's about epistemologies, ontologies, but not in philosophical way, but very hands-on, practical things that can be applied. And some of them are applied in industry. So we have new products, new services already launched in these 10 years. Yes. Yeah, I mean, it's really about how do you organize, who gets, you know, a chair at the table to produce new knowledge, new understanding, and then from that out, new innovation. And just for example, we have one of these residencies at the European Space Policy Institute. So we're with Kyria Kigoni, artist from Athens here, thinking of how space policies should take into account more cultural understanding, more diverse understanding of the space sector as such. So we have this kind of collaborations, yes.
I have a question. I was in a presentation a couple of years ago in FOSDEM, and like the whole title and the meaning is that the open source software won. And now we are everywhere, and now like Google, Microsoft, everyone uses open source, everyone contributes to open source. But I think that the thing we think about open source is not winning, actually, and is what you said about the way of organization and the whole development of things. And my question is, what do you think, how we can like focus again in this thing? Because now open source means like what Google and Microsoft says about open source, like big companies contributing code and not about development, not about communities, not about like what we think about open source.
I mean, so at VAG we are addressing this by more focusing on the narrative of community-driven. So we don't focus on solely technological narratives. So it's not about the code and the source anymore, but it's more about community-driven technologies. We even say it's more about concern-driven technologies. Because if your concern is IP or autonomy, so you develop completely different technology than if you are benefit or profit-driven technology. So in this way, the focus of the narrative and the way you imagine everything is not technological, but is the way we are organized and the way technology matters to us. So that's why we prefer using community-driven or concern-driven or even justice-driven technologies, because that's what we're looking for. The end goal is not open source. The end goal is more public use of infrastructure or more public infrastructure, especially in the space context where public notion is hardly hardly present. Also because most of the legislation is on the level of international law and not national or public law. So that's why bringing space technologies to the public discourse, where the public is not just a gathering, but it's a gathering of people with concerns, then it's way sharper. And that's how we got to the, let's say, to the Fediverse, especially in the social media context, where technologies are organized in completely different way. So you can have your own server, run your own platform, and no one can enforce you how to do stuff. So in this way, I mean, that would be my answer in this context. If you have any other questions later on, we are around. Thank you.
So we have a presentation that we had those presentations that were missing. So Jose had already a presentation, and he will talk about how to hack a satellite, as I just saw. Yeah. So thank you, Jose.
Thank you. Just 1 second. We need to plug in my laptop here.
Yeah.
I have an adapter if you don't. Okay, perfect. Okay, perfect. Yes. Here. Perfect. Let me make this full screen. Yeah, you can tell it's PowerPoint, not LibreOffice. I'm very sorry about that. I think we go like this. Can we move? Okay, perfect. Yes, so hi. Hello, everyone. My name is José Manuel Díaz. I'm a hardware and software engineer at the TU Berlin. And yeah, I'm here to give you a little bit of an impromptu presentation that I actually prepared for a different event called the Wacken Open Air Festival. It's a metal festival. And this year we had a space camp. Actually, the whole festival was space themed. And yeah, I decided to talk about how to hack a satellite. And I was actually telling some of my friends, yeah, I have this idea for a talk. I'm going to explain exactly how to hack a satellite. And they told me, oh, are you sure? Is that, are you allowed to tell this? I'm like, yes, definitely. And I'll give you a lot of detail. So hopefully it's interesting for you. Yeah, but before we start, I would actually like to ask you, the audience, some question. So I'll show you some pictures and some prices. So this server, let's say it's from a bank or your email provider. Let's say it costs 100,000 euros. And I would like to ask you, how difficult do you think it is to hack it, or how easy it is to hack it? So please answer. Easy, difficult, yeah. Sure. Medium, okay. Medium difficulty. Any other answers? Easy. Okay, easy. Hard if it's technical. Sure. So I would say it's actually very difficult, considering the context that I'm going to talk about later. So we assume that they have proper security teams, and we assume that they're competent. So okay, we're going to say it's very difficult. Okay, I don't know why this is not showing in the screen here. It shows for me. Okay, maybe I need to reload the page. Ah, okay, that's why. So let's accept this. I'm sure I agree with everything that they're telling us here. So, sorry for the interruption. Come on. Technical difficulties, of course. Cannot get away from them. Yeah, loading the presentation. Presenter view, please. And I would like the other window. Great. Okay, hopefully we're back on track. So, okay, so we say it is very difficult to hack a server. What about a laptop? What about your personal laptop? How difficult it is to hack it, do you think? Difficult? Yeah, other answers over there? Difficult? Sorry? As an individual. Quite hard? Yes, I would say it's maybe easier than a server from a big company, but we also assume that operating systems for laptops have some security built in. What about a mobile phone? Actually harder than the laptop? Well, that's actually correct, I would say. So yeah, mobile phones, Android, iOS have one of the best security architectures. Every application is sandboxed and yeah, very difficult to hack. Okay, what about something like a GPS satellite? How easy is it to hack it? Quite easy, okay. Yeah, keep in mind it's a military satellite, so yeah, I would say GPS satellites probably very difficult to hack. Yeah, okay, yeah, we're not talking about breaking cryptography. Okay, we say it's very difficult to hack. Now what about something like this, a satellite from the TU Berlin, costs about 15 million euros. How easy do you think it is to hack it? More difficult than the GPS satellite?
I might close to the antenna of TU Berlin.
Yeah, well, how close are you to the antenna of the TU Berlin? Very good question, we'll get to that later. Right. Harder. Okay. Replay attack, okay. Well, okay, clearly, okay, this presentation was prepared for a more general audience. Yes, it is. Oops. It is actually easy to hack this kind of satellite. And also, this is a satellite that I worked on, also easy to hack. And this should be surprising to people. So I'll now tell you exactly step by step how to hack a satellite. So the first step is to build a ground station. When you think of a ground station, maybe you think of a big antenna like this. Then the next step is to do a lot of research. And I would say that this is actually the hard part. You have to find out information about how the command protocol works. And there's many sources about to find this information that I'll talk about, and then you do your attack. So step one, how to build a ground station. Yeah, again, you look at this and you think, wow, that's pretty expensive and probably quite difficult. But actually, my point is that it is easier than you think. And here are some thumbnails from one of my favorite YouTube channels. It's this guy that builds, equipment to talk to satellites from, discarded equipment. Yeah. So how do you do it exactly? So first, you need an antenna, very cheap. You also need an RxTX switch, something like an LNA, and a very cheap software-defined radio, and something like a Raspberry Pi. So this is all pretty affordable to receive from a satellite. To actually transmit to a satellite, oh yeah, of course, and GNU Radio, one of my favorite pieces of software. It's free in all senses of the word. To transmit, you also need an SDR that is capable of transmitting. This is maybe a bit more expensive. And finally, you need a power amplifier. So this is also a bit expensive, but in the end, it is something that you can buy as an individual, and it's not that complicated to put all of this together. Yeah, so to research your target, kind of what is the information that you need to find out the command structure and the telemetry structure. So the good news for us is that a lot of all amateur radio satellites are required to publish a lot of information. maybe not the command structure, but you can be creative and think that there might be some symmetry in this and reverse engineer, and also some other ways that I'll talk about. So how do you do this? Well, you go to SatNox, and I'll show you what that looks like to find this kind of information. Another method is, signal intelligence. I'll show you what that looks like. And you do some reverse engineering, which is a little bit outside of the scope of this presentation, but there's people that are extremely skilled reverse engineers. So this is kind of what, the information, how it looks like for the satellite that I was involved with recently at the TU Berlin. So actually I think this is a pretty good visual overview of kind of the framing structure and the fields and what it contains and so on. We also find some very interesting telemetry parameters, so things about the thruster, what temperature it is, and so on. And yeah, this is all great for an attacker. So how does it work to get information from SatNox? Well, you choose the satellite that you're interested in this case NanoFF. You see the observations that were just recently received, and in some cases, maybe you're familiar with this, you can see that in some cases we have even decoded data, so we click on one of those, we see, okay, this is what the telemetry or what the radio signal looks like, and this is kind of what the data looks like. If you look at this for the first time, you think, okay, well, this is just some numbers, I don't really see what I can do with this. But if you have some reverse engineering friends, they can make sense of this and figure out how to talk to the satellite. The next thing that you might want to do is exactly what Elkos mentioned. You go with your recording equipment to the ground station of the satellite that you're interested in, and you make some recordings. So this is what you might see. So here you see the satellite signals, a bit weaker, of course. And here we see the ground station signals. So we zoom into this, let's say, and we see something that looks like this. Okay, this looks like some digital data. So we have multiple of these commands, and we can start to figure out what these commands do. We look at the telemetry. Okay, when this command is sent, this change in the telemetry. And step by step, you can figure out how to actually make the satellite do what you want. Okay, so you now have this information. What can you do with this information? So I have some ideas here. The first thing is you might want to use the satellite to take pictures of some interesting locations on the Earth. You can use your imagination. Maybe more interesting, if your satellite has a way of changing its orbit, you might want to do some orbital maneuvers, and yeah, I'll show you what that might cause in a second. And kind of the next thing that I imagine is actually something that I'm personally scared of. So this is a jammer, and yeah, we've probably all heard the news of GNSS jamming in Eastern Europe and how much disruption that causes. Now imagine you do that from space, so pretty bad. So how do you take a picture? Well, actually, you look at the time that your satellite will be over the area that you're interested in. You tell the satellite to point towards the Earth at that time. You take a picture, and you download the picture. Okay, so this might be what it looks like, your command list. This is also like a typical task that a student operator might do, so it's not that complicated. Okay, this is very exaggerated, but what might happen if you choose to do some orbital maneuvers? I'll take the sound off, and thankfully Hollywood imagined this for us. So while you crash into a satellite, all the astronauts are floating around. Yeah, this is very exaggerated, but actually it is something that you can do if you misuse the capabilities of a satellite that can change its orbit, right? So how do you do that? It's a bit more complicated. You have to do some math. This is a Hohmann transfer. It's a standard maneuver to change your orbit to a different one. you have to calculate the amount of delta V that you have to change from your current orbit to your target orbit. So you plug in some values to this calculation, and you create a command list that looks like this. Maybe maybe the satellite that you're interested in has some kind of password to enter the special mode to do dangerous operations, but with the steps that we talked about before, you can figure it out. And okay, how do we do a GNSS jamming from space? Actually, I'm not going to tell you how to do this. You can probably figure out yourself. We're all smart people in this room. But this is maybe something I don't want to talk about because I think you can do a lot of damage with this, and also in a way that is difficult to determine who did this. And you might ask, okay, if these satellites are capable of causing so much damage, why are they easier to hack? So we have maybe some arguments. This kind of new space field that we're all part of has grown really quickly in the last, let's say, 10, 15 years. And on the other hand, terrestrial computing, so servers, laptops, mobile phones, kind of exploded in popularity in the 1970s. So we can say that they've had something like a 50-year head start in security. And then there are maybe some other technical reasons. So to actually have proper security, you need some hardware features that might be available in embedded systems, but then you're restricted to the specific platform. And there's also another thing that we were just talking about at lunch. Adding these kind of security measures also poses an operational risk. What happens if you lose your encryption keys? Maybe your satellite is still working perfectly fine, but you cannot talk to it anymore. And there's no shared software base that manages this for you, so you're afraid of making a mistake, especially if it's the first time that you're working with this kind of technology. Okay, so hopefully I've convinced you that this is a problem, and I would also like to talk a little bit about our idea for a solution. Actually, I'll talk more about this in my presentation tomorrow. We are working on an operating system for satellites that uses standard space protocols and technologies, also built with memory-safe programming languages so that you don't make the typical mistake that you might do when programming an embedded system. And our idea is to make this be kind of the standard way of securing your applications. We have some missions that will use this operating system, which again I'll talk about more tomorrow. These are just some pictures of the satellites. And in short, we are founding a non-profit organization to manage the intellectual property here. We plan to license our software as GPLv3. And we are definitely looking for people to help us with this. And with that, I ask you if you have any questions.
So is there not any danger in changing the orbit of the satellite?
Definitely. It is. You have to be quite careful when you do these maneuvers for, let's say, a proper purpose, not trying to harm something. So it is definitely dangerous, and is something that an attacker can use to cause chaos in some way. Yeah.
You mentioned changing the orbit of a satellite. To my recollection, most CubeSat class satellites that would be more easily susceptible to such maneuvers don't use actually CCSDS protocols. I don't remember the proper book right now because I'm too tired. But the issue I kind of think is that satellites that are actually capable of orbital maneuvering, at least to my understanding, I hope are implementing proper encryption systems due to the unique challenges and dangers of orbital maneuvering, I hope. But in another case, when you said that what's a bad thing you can do, it's actually putting the satellite in a spin mode.
Yeah, that only harms your own satellite. So this is a kind of a denial of service. This is also something bad you can do. To answer your question, or but basically I agree with you. I hope that satellites that have these capabilities also have any security mechanism, but this is not necessarily the case. It will be required by upcoming EU space regulations, and also the thing is that CubeSats are getting more capabilities, and the example I showed you with NanoFIF are 2-unit CubeSats that have a propulsion system, and I am not able to comment if they have encryption or not. So.
Okay. So,
yeah.
I don't feel comfortable right now.
Yeah.
It doesn't make sense to it doesn't have the capability to change so drastically the trajectory.
Sure. But
you cannot increase your orbit, let's say, kilometers to
sure.
ISS.
Sure. Right. Sure. But you can also do something called differential drag. So even without a propulsion system, you can change the relative aspect ratio of your satellite to in the flight direction to lose velocity. And this is a way to change your orbit without using fuel. And with this, you could have a satellite that is in a higher orbit than the ISS and then fall down to the ISS and, I don't know, cause them to maneuver, for example.
The capabilities for budget terrorism using that approach. Do you think that it would be ethical to have a group that does, I mean, something sanctioned by the EU, for example, that actually hacks available satellites and either secures them or destroys them to avoid them becoming assets of an attack?
Yeah, that's an interesting question. So if there should be some kind of a state-funded group that hacks satellites that are vulnerable and they're dangerous, I don't have an answer for that. It definitely sounds like a good idea in a sense of protecting the space environment or the people on Earth, but it's also somehow harming private property. Yeah, definitely interesting question. Maybe I would say I'm not going to decide that. But yeah, interesting idea. Yeah, please.
We are kind of short in time, so let's continue the discussion
yes,
after.
exactly. I'll be outside. So.
So we're back on track with Xavier's presentation. Xavier has been collaborating with LSF for many years on several projects. He is now leading SC Robotics, a Spanish company specializing in remote monitoring solutions. As an electronics and space enthusiast, Xavier is always exploring new projects and ideas that can be applied in the space, within the space industry. So let's welcome Xavi and shed some light in light pollution.
All right. While Freddy fixes the issue. Well, yeah, my name is Javier Crespo. I'm from Spain. I work as a company called SC Robotics. We design remote monitoring devices. And today we want to discuss light pollution, which is almost, it's somewhere in a virtual screen. Yep. All right, yeah, so thanks, Freddy. Thanks, Mantos, for the introduction. And does it work? Yeah. So yeah, as you know, light pollution is a big issue. It's an ever-growing issue, and it's actually true that the awareness, the public awareness, is also increasing, but sadly enough, it's not increasing as fast as the issue is rising. So light pollution, it is an issue for many reasons, biology reasons. It affects the circadian rhythm. For ecology, for instance, the bird migration routes are affected by light pollution. There are actually some great resources online trying to track these bird migration routes and how, for instance, big cities and the lightning of big cities, they affect how they navigate from one place to another. It's also, there is some author coining this term noctalgia, which is a loss in cultural identity, because a while ago, decades ago, our parents, grandparents, they could see the stars and they could name stars, and that was easy. Now it's not that easy anymore. But anyway, the reason why we're here, it's because we like space. So, of course, light pollution is important because it affects astronomy, both amateur professionals like everyone, and other fields such as optical communications, which is increasing, like it's a big trend and it's a big thing. It will become bigger in the next year, in the next few years for a few reasons, special security. I think there's a poster over there about optical communications, very interesting. So yeah, light pollution, it has to be taken into account for this. So yeah, a few years ago, the European Space Agency, they granted Libre Space Foundation a project called Optical Makerspace. And in this project, the idea was to design or to understand the field. So they set up smaller projects exploring different issues, different areas. So for instance, we designed, actually, that was also my company, we designed a controller for a telescope mount to track satellites instead of stars, because they are, well, it's different orbit parameters. We also, there was like some sort of integration between SatNOX and optical ground stations. We upgrade, or actually LSF upgraded some stations to support optical communications. And the last activity is wanted to design a device, an open source device, to monitor sky quality. And that's how we designed what we call the dark sky meter. So we designed this device. This device, it's an autonomous device with a solar panel and. Well, yeah, it's an autonomous device with a solar panel, a battery, and it has a few sensors. It has obviously a light sensor. It also has a temperature, pressure, and humidity sensor inside the enclosure, because at some point we want to use it for fine-tune the calibration. at the moment, it's useful to detect if there's water inside the enclosure, because it's a tricky part of the design, the sealing. It also has an accelerometer, because you want to make sure your samples are taken or were taken when you're pointing to Zenith. And in terms of connectivity, well, the main MCU is an ESP32, so that's Wi-Fi connectivity, but we have expansions for cellular and for LoRaWAN connectivity. A bunch of other interesting features, but the point is that we ended up designing this open source firmware hardware device, which is able to measure light intensity and push it somewhere. So, yeah, this is one of our test tables. We have now manufactured over 200 of them. That's what the data look like. On top, you have the battery life. So the device, how it works is during the night, it will take samples every 5 minutes. One sample takes roughly 1 minute, because you have to take a lot of samples to do some sort of calculations and to depending on the gain that you want, and to the data quality, basically takes one minute to take all these samples. So that means it's awake like 20% of the time. During the day, of course, you can just sleep, or you can reduce drastically the sampling time, which is what we do, because we like to know that the device is alive, basically. But you can see that during night, battery drops something like 10%, and that means that battery, even if there is no direct light, it will last for roughly 2 weeks. In the middle, that's temperature inside enclosure. I think that was winter, yeah, January. So it was not bad, from -10 to 30 degrees, but it's actually usually from -60 degrees to -20 degrees. So the point here is the conditions are quite harsh, and you can imagine that you do not want to put this device in the middle of the city, because it doesn't make a lot of sense. You want to put this in the middle of nowhere. That's where it makes more sense. And yeah, well, the last graph at the top, that's the light intensity. You can see that during day the light saturates the sensor, and during night, well, you can see some stuff there. That's one of our devices after 1.5 years being deployed in the field. And what I want to say here is that we have designed something really reliable, really robust, because even though this device looks really bad, it was performing really well. Like, the battery was also like every day between 100 and 90%. And something important here is like this glass that's covering the lens. That's a BK7 glass, a special glass to avoid, to minimize the degradation of the glass, and to ensure that the performance of the optics is good and will not degrade during time. And in this case, it was perfect. So this says, okay, so it's loading. Well, it's just a GIF. We don't care. So we have all this data, and what can we do with all this data now? So basically, our customers, they have their own platforms, and we started looking around, what can we do better? There are a lot of platforms. Some of them are like for single measurements. So you go outside, you take one measurement, you upload the measurement to a platform, and then you have a platform which collects measurements maybe from 5 years ago, one measurement. That's, well, not really smart. There are platforms that have a lot of data from a given location. For instance, in the Netherlands, there is one interesting platform with a few different sensors. A lot of them are inactive or outdated, and the worst of them, they are unlicensed or restricted licensed. So we think we can do better. We have designed an autonomous device which you can put in the middle of wherever you want, and it will take measurements for you. You have to do nothing. We want to work with LSF to create to leverage their SatNox community and create some global platform. And of course, it will be licensed under a copyleft license. But there are some challenges. As I said, the devices are in a really rough condition, and they have to be really reliable. The community, this kind of crowdsourcing communities are, in the long term, it's really to maintain the engagement, and usually after all the buzz is gone, they go down, the activity. So this is something that we have to actively monitor. And there is a big part here, which is the optical calibration. Well, regarding the reliability, I think, well, we have more than 200 devices now. We have gone through several iterations of the ceiling, which is the main thing here. And I think we have solved that issue now, but it did take a while. Regarding the community, well, we have LSF here, so they know they have been doing this for years very successfully. So, yeah, we have to use that. Regarding the optical calibration, the only thing that I can say is that we intend to collaborate with scientists as much as we can, but we also have to say that sometimes scientists have different goals than engineers. So maybe the data, the quality is not what they want, but maybe it's enough for us. So that's something that we at least intend to actively discuss with them. So this is Open Dark Sky initiative. So there is a platform, Open Dark Sky platform. There are the devices and there are the users. So, and that's, of course, LibreSpace, my company SC Robotics, and the community, which in this case is you, and even the scientists. Regarding the platform, there is already a platform live. It's available at map.opendarksky.org. And, well, it's a really alpha version because we wanted to have something ready for this talk. But you can see some devices there. We will get there, but something to show there. Of course, open source. You have also the link to the source code below the picture. The devices, we have designed, so the one at the left, on the left, you can see there, is the one that I was showing you. Everything is open source, but that doesn't mean DIY, because the mechanics are tricky to do. You need special equipment, special materials. So we think we can have like a more DIY-friendly device, which we are, well, looking forward to have your feedback, which is the same device, but simpler mechanics, so you can do that in your home. Again, source code is below. I have the devices, a few of them here with me, if you want to have a look and discuss later. And what do we need? So this is a QR code to our matrix room. Please feel free to join us. We are looking for feedback. We want to know you. We want to know what do you want the devices for. Where would you put them, the location, because we have like Wi-Fi, cellular connectivity. What do you need? Are you an institution, an individual? Would you like the pro version, what we call pro version, or the DIY kit? We basically want to understand all of you, and we will figure things out together with you. And that's it. All right, I was fast. Yeah, so that's the link to opendarksky.org. The QR code will take you there. And this is a collaborative initiative with LibreSpace Foundation, SC Robotics, and European Space Agency. And yeah, let us help us fight light pollution. Thank you very much.
Thank you for the presentation. Can I just ask you, how much data is there on the open dark sky? I mean, how far back does it go? And what's the coverage?
Actually, there is no data, I'm not going to say no data at all, but as I said, our current customers, they have their own platform, their own data, and it's not available on this website. So that's why we decided to launch this other website. So at the moment, let's say there is no data. Not true, but pretty much.
But do you also maybe match your observation with the Earth observation data?
That's interesting, and at the moment we don't, but yeah, that's something that we will have to, at some point, we will have to take into account and that we can do. We were discussing at lunch, you can actually measure light pollution from Earth to space or from space to Earth. Different trade-offs, and we are focusing on the devices, so Earth to space, but we think this should be taken into account in the future.
So, I mean, we have an example of pollution observation, both directions, also with the citizen sensing network of dust particles. So we would be interested in, this sharing the Earth observation and ground observation.
Okay, yeah, we can have a chat later.
Super, thanks.
Okay, thank you. This was very interesting. Actually, we were promoting this poster about optical communication, and we did some campaign in the center of Portugal, very near to Spain, actually, in the dark sky region, which we selected because it has excellent conditions and has an excellent sky. So the questions you raised, how confident is the data, and the databases is very, very relevant, I think. It could be very interesting also to think about expanding this to image-based method, because for everything which has to do with optical communication, at least, what's very important is the contrast between the stars and the non-stars regions, which can serve as some indicator also of light pollution. So I know that there are also open source or open citizen initiatives for asteroid observation, for instance, or for all sky cams, this kind of things, which can also be implemented with some moderate budget. And I think would be very interesting to also to cross this information with your method, which is very, very interesting. Yeah, thank you.
Yeah, that's true. As I said, right now, like this data is being used for scientific purposes, and we think we can cross like information, as you said, with the imaging or with other like asteroid tracking stations, and with all of this together, we think we can provide a better, in the end, better data for everyone, and we can do. For instance, optical communications, it's something important to track the light pollution and to make sure your ground station is located in a nice area.
Hi. So you showed a price of under 200 euros for the DIY kit, and I was wondering if you took into account the possibility that someone who builds a DIY version of your device may deploy it somewhere where they will have access frequently so they can maintain it. So if you find ways to cut the cost based on that.
Yeah, I mean, these are estimated prices for low quantity orders. We don't know the magnitude that we usually, in my company, we build batches of like 50, 100 devices. Of course, if we order like 5,000 tomorrow, the cost will not be 200, but I'm not sure we will have 5,000 geeks like me ordering these devices. So yeah, we have to take into account that. All right, thank you very much.
We're going to have a break, exactly 20 minutes. So.
Sleeping? I'm already sleeping. Tonight we're going to terrorize your hackerspace. Tonight we're going to terrorize your hackerspace. Are you? Yes, of course. I don't know how we'll make it to my hackerspace. How will you?
Listen a minute to Kitty.
Baby, let him go to bed.
Let him go to bed. Out of sight, out of mind.
So, are we starting the last presentation and the last session? Okay, let's wait some. Yeah. So, Clemens will do the last presentation for the day. Clemens is a flight dynamics and software engineer by day at TU Berlin and freelancer for Libre Space Foundation by night. And he will do the most dramatic presentation today because has a live demo. So yeah. Be ready for blue screens, yeah?
Thank you for the introduction. Yeah, it's the last presentation of the day. I hope you won't fall asleep, but yeah, it's quite a short time for a live demo, so brace yourselves, it's gonna be a bumpy ride. Okay, so first, this presentation is a Jupyter notebook. It will be available after on the conference website. And maybe it will be available also on the Ephemerista repository, not sure yet. Some cells are hidden because it's exported, and I wanted to keep some information out because it will be too much for the presentation. But if you open the Jupyter notebook, you will find some more information, some more code. And there's a link to the repository where there are other example notebooks to demonstrate all the capabilities of Ephemerista. So the origin, it started as a project called OSCW 2 years ago, funded by the European Space Agency. And the aim was to design and develop an open source satellite mission and communications analysis simulation tool. The prime contractor is LSF. In the first phase, the project was developed by a team of freelancers for LSF led by Helge Eichhorn. And also, I forgot to mention ST Robotics. And the second phase, which is hopefully will take off, is community building. So there might be some more funding for development, but the idea was at the end that the community uses it and contributes back to it because it's licensed under GPL v3, so strong copyleft. Any use of derivatives of the library have to be open source, so people have to contribute back. So basically, the project is, let's say, a trinity of a Python library, an API, and a web GUI. And telecommunications and constellation oriented. This was originally in the ESA core. So the architecture, initially the idea was to use polyastro as the core for astrodynamics computation, like orbit propagation, etc. But bad news, both maintainers stepped down, and the code is not maintained anymore, although there's one fork called Hapsira, but the decision was made not to continue using polyastro for Ephemerista because of the large code base and technical heritage. So that was a big issue. What are the alternatives for reliable and fast astrodynamics computation? Because you need propagation, you need timescales, transformation frames. So the two alternatives that were considered was using ORCID, which you probably heard. It has, it is in Java, but it has a Python wrapper. And the second alternative was to write a new library in Rust. And yeah, the meme on the left, it's basically shows how hard it is to have some libraries in a small, like open source libraries in the space sector, because it's very small and sometimes a project depends on only 1 or 2 maintainers. If they step down, the project collapses. So then there was a choice, which I stole from Helge's presentation a few weeks ago at a Rust conference. I put the link. Is either use your Java library in your Python code, maybe not super pretty, or you write your own in Rust. And I'll explain why. We did both. So first, we used OREKit, so it's Python wrapper as a gap filler, because it's a well-verified code with a large community, I mean large for the space sector, and a pretty good performance with some bottlenecks. And then, basically Helge is a big fan of Rust. They wanted to develop a new library called Logs, which has a better performance than the OREKit Python wrapper, and also the advantage is you can seamlessly integrate it into Python, and Rust is safe. So the architecture looks like that. So at the bottom, it's a bit Frankenstein. You depend on 2 core libraries for astrodynamics computation, but as more and more features are available in Logs, these features from OREKit are not used anymore. And there's also one argument for OREKit is that I'm quite involved in the OREKit community, so I'm a developer and also quite some experience using the OREKit Python wrapper. So in the middle you have the ephemerista Python library, and it makes the objects available to a fast API, because all the classes are Python-t classes, so it's very natural transition to fast API. And on top of that, there's the web GUI, which is written in, I really don't know about it, but JavaScript and TypeScript, I think. So the first part is this Logs Rust library. I was not involved in development. I'm not a Rust developer yet, but it looks pretty cool, and the performance, from what I've seen, is impressive. And it's made available to Python using the PyO3 project. So here's the link to the GitHub and the talk by Helge at the Oxidize conference in Berlin a few weeks ago. It's definitely a must-watch, because they mentioned also ephemerista. And so the second core library we use is OREKit. So like I said, it's open source using Apache 2, so it's very permissive, so no problem to use it in our project. First problem, in the time where we started the project 2 years ago, there was only one Python wrapper, which was available only on Conda, Forge, and not on PyPy. And yeah, that's a big issue, because if we want to publish ephemerista on PyPy, it's upstream dependencies too. So there was a solution. So the OREKit Python maintainer, Petrus, had started work on a new wrapper, which is based on the JPy project. And we helped him making it ready to publish on PyPy. So I don't know when was it 2023, 2024 that we finally published the new OREKit JPy wrapper on PyPy, and then we could finally upload ephemerista on PyPy. Yeah, remaining issue. You need Java in your Python project. That's not pretty, but there's a solution. It's called JDK for Py, and you can package a JDK in your Python project, so installed by pip. There's still one issue. So OREKit Java in itself, it's quite performant. But if you use the Python bridge, there might be some bottleneck. Like if you rely heavily on loops, if you do a loop with 100,000 iteration, it's going to be pretty slow. And there are some times where you can avoid loops using OREKit, but sometimes you can't. If you want to retrieve all the intermediate state vector like position velocity for 1 year, it will be super slow. The solution we found was writing some code in Java to retrieve this data, and then compile the Java code, and you pass the jar to your Python project. It's possible thanks to the JPy project. It sounds scary, but once you did it, it's actually quite easy. So some of the features of the ephemerista library are like typical astrodynamics features. So you have timescales, reference frames, some propagators, so SGP4 for two-line elements, TLEs, and then semi-analytical and numerical orbit propagators based on ORAKit. Event detection is important, for instance, for detecting passes over a ground station. Spacecraft and ground asset modeling, so you model spacecraft with some properties, some communication systems, etc. Same for the ground station. And then with that, you can build a link budget, which is, in my opinion, one of the strongest features of Ephemerista. And the goal, like I said, was to design constellation using this tool and then to optimize the constellation. So like you can run some analysis of the constellation and optimize the number of satellites or optimize the communication systems like the antenna gain, I don't know. And it has a web-based GUI that I will demonstrate live if it doesn't crash. So using this web GUI, I mean, deploying it is as easy as running a Docker run. If you use Docker, it's super easy. I did it on my home server. It worked right away. You just need to download a bit of data that ORAKit needs, and like some ephemeris data. Or you can use Docker Compose. This is an example of Docker Compose file. And here are some useful links. So there's a website, there's a matrix chat, and then these are the repos and the PyPy links of the project. So now I'm switching to some code demonstration. So the basics is basically to import the library, to init some data that you need for the library to work. And then the first thing you probably do is to propagate a two-line element because it's one of the most common way to represent a state vector. So this is the ISS orbit. You define a propagator, you define the start and end time, and then you propagate and you get a trajectory, which is a collection of state vectors. So it's very short. I mean, it's quite basic, but if you use some other tools like, I don't know, the ORAKit Python wrapper, which is really great, but because it's Java-based, you will require more like 50 lines of code to do the same. And then it has some plotting features. So it has, for most of the plotting, both Plotly and Matplotlib available. So I prefer personally Plotly because it's interactive, but Matplotlib is more standard, let's say, for publication. You can plot some ground tracks, again, both in Matplotlib and Plotly. And here's an example to model some ground stations. Here, these are some S-track stations from ESA. And you just define your list of stations. Maybe I go too quick, but you don't need to understand all the code. It's to show the general ID, and then you can take a look at the Jupyter notebook yourself if you want to go deeper. And here you can do the same ground track plot while showing the ground stations. Okay, so now I will show how to load a scenario and to compute visibility event, because propagating is nice, but you want actually to do some useful stuff like computing ground station passes and do link budget. Because we're using Pydantic for all the data classes, it's easy to serialize and deserialize data into JSON, so actually you can export and import all your spacecraft or scenario from and to JSON. So here's an example of a JSON file. So this is a lunar mission, and it looks like that. So you have a version, because that was one of the requirements to be able to versionize the code, of course, but also the JSON file, so that if you load an older version or a newer version of a JSON file with an older version of the library, you might get some breaking changes, so you will get an error. Here you get the start and end time, the time step. And then the assets are the ground station or spacecraft object. So here, this is the Cebreros ground station, centered on the Earth, latitude, longitude, altitude, and minimum elevation to track the satellite. And then you have the spacecraft. Before we used the TLE for the state vector, and this time we actually use an ephemeris, which is already pre-computed from a CCSDS OEM file, which is one of the standards to represent the spacecraft trajectory. So here, yeah, it looks ugly, but basically you recognize the orbit is defined from CCSDS file. So here you load this JSON file that we just show, and then you say, okay, I want a visibility analysis. So visibility computes all the visibilities between all the assets, so all spacecraft and all ground station. You analyze. Okay, here I showed the time it takes, like 2.5 seconds, but you have several assets, and it's during 1 month, so it's quite fast, I think. So here you select your spacecraft, which is on the lunar transfer. You select your ground station, and you collect the pass data. So here you have your list of ground station passes. So basically you see once a day a pass which lasts almost half a day. It's normal because it's a spacecraft on the way to the moon, so the passes are much longer than LEO spacecraft. And then you can get your range data or range rate, which is very important to compute your Doppler shift, for instance, and then azimuth elevation for your ground station to track the spacecraft. Yeah, so this is using matplotlib. Looks pretty neat. Okay, next example, the link budget. So the link budget can be done with and without interference. This was also one of the requirements. We have more and more spacecraft in orbit, mega constellations, thousands of objects, and not all of them comply with the, let's say, regulations, or even if they comply, you have some let's say, side lobes, some splitting of some residual radiation on the side, and it might cause your ground station to receive some interference if it's in the same frequency band. So here you do the same as before. You load a scenario that either you create in Python or you load it from a JSON file. You analyze it, and then you can gather some data from the link between one station and one spacecraft in this case. And here you see the duration of the pass. These are like a few minutes pass, so it's a LEO spacecraft. You see if it's uplink or downlink. You get the mean slant range and some more data that doesn't fit on the slide. It's a big pandas data frame. And you can see the detailed metrics of a single pass. Here the time step is 1 minute, which is quite rough, but you can have it with a lower time step. So here you see the slant range lowering and then increasing again, and you get useful metrics of a link budget like free space pass loss, radiated power, etc. And then you can plot this data. So this is the same data, I think, as in data frame before. So you get the range, you get the transmit power, the receive noise, etc. Maybe it doesn't tell you anything, or not all of it makes sense, but basically it's most of the data you see when doing a link budget. And at the end, what you want to see if your communication link has a margin that is positive and large enough to have reliable communication with the data rate you want. Or on the other way around, you want to optimize your data rates while keeping a certain margin. And then you can do the same with another spacecraft. So there's the notion of tracking. So you can tell a spacecraft to track a ground station and the other way around. And you won't get any angle losses because of the pointing of the antenna. But if you don't track the spacecraft, you would get like an off boresight angle. And then the antenna will have a lower gain because it's not in the main lobe of the antenna. So all of this is taken into account for the computation of the link budget. And there are also environmental attenuations available based on the ITUR recommendation. So this is using the ITUR Python library. So these are the usual attenuation you consider for your link. So it will drop by maybe 1 or 2 dB depending on the frequency, depending on the probability of exceeding. And then there's the same with interference. So it's a bit harder to model, but basically you have all the same here than before. It's just at the end, your signal-to-noise ratio will be reduced because you get additional power which flows into your noise because it's not a signal you want to receive. So in this example, it gets reduced by 5 to 10 degrees, and as a result, your link margin too. So this can be quite damaging. I forgot to mention that these computations are verified against MATLAB. So MATLAB is also able since a few years to do this kind of link budget and interference analysis. So we verify our data against MATLAB. But our implementation is cooler than MATLAB because it's Python. So a conclusion for the link budget before, and maybe some of you did, I was using Excel for link budget, and it's really awful because it's hard to manage the versions. Like you can check out your Excel in a Git, but it works pretty bad. And at the end, you have like 15 versions of your spreadsheets. So if you use Ephemerista for link budget, you can have it version control in Git. You can run it in your CI/CD pipeline. Like, yeah, you can directly check what are the changes on your link budget depending on the change on the orbit or on the spacecraft. And you also can run thousands of simulations very quickly to optimize your ground segment or to optimize your satellite. Another cool feature is the coverage analysis. So you want to compute which areas of the Earth are covered by your spacecraft. For instance, if it has a camera, how often do you see it and how often you don't see it. And I skipped most of the cells here. I just wanted to show the results. So there are different ways to split the Earth into small regions, so using different libraries. And this one is using rectangles, and so you split the Earth. Here's pretty large cells because I wanted it to run fast. And then you can just compute which areas are visible by the spacecraft during its orbit. And at the end, the average percent that the cell is covered during the mission time. So this is for one orbit and for just a given section. You can do it for the whole Earth, just takes a bit longer. And you can plot the other way around, the maximum duration without seeing the spacecraft, which is usually what you want if you have a region, I don't know, you want to observe a wildfire and you want to guarantee that your satellite will pass at least once a day. This is the maximum time gap that you want to compute. And so here you have this area with 0 because the spacecraft doesn't pass over it, and these you have basically 6,000 seconds because it only sees it for one orbit. You have to wait one orbit to see it again. This is the same plot, but for 5 days. So here is an example also of retrieving a geodata frame, which is one of the standard data to work with tabular data and geolocalized data. So you get a geodata frame with your geometry being the polygons that you split the Earth into, and you get your coverage person, maximum time gaps, etc. And because it's a standard, you can then export it to whatever tool, geo tool that uses also geodata frames. So then the same plots for this 5 days analysis, and then you see that the northern, the high latitudes region have a higher coverage than the equator, which makes sense because it's, I don't know, maybe it's a polar or maybe ISS orbit, I don't remember. And then the same for the time gaps, and you can see it looks a bit funky. Some areas have very long waiting times, and some areas much lower. Okay, so that was a bit long. So that was the Python part, and now I will do a small demo of the web GUI. Okay, so I already did the Docker compose for you because it can take some time if you need to pull the latest version of the container. But basically it looks like that. So you have an empty scenario here. You can load a JSON file if you want here, which is very useful to see some examples. But I'm going to show you from scratch. You have a spacecraft, like the default one uses the ISS orbit, so I will keep it like that. And then you just click on propagate, and it will propagate the orbit. Okay, network error. That's why it's a live demo. Okay, so probably the container doesn't run anymore. Just 1 minute, calling technical support. Okay, I restarted the Docker container. Needs a few seconds to start. Here we go. Okay, so now we have a web GUI, so it has the ISS orbit. You propagate, and then you see here the Earth, and then you can change the time faster or slower, and then you see here the orbit. Okay, and I'm already, I think, over time. If we want to have time for questions, I will just show maybe constellations because it's quite cool. So here I created a default constellation, which is a type Walker Delta. We have 4 types of constellations available. I will just use the default parameters, so it's basically at the same inclination as the ISS 24 satellite. And then you click on Propagate to. It will take a bit longer, but it uses the semi-analytical propagator, which is using ORCID, and it's quite fast because it's a bit slower than SGP4, but faster than a numerical propagator. And then you see here you have your constellation of 24 satellites. And the link budget and coverage analysis, so basically all the features that are available in the Python library, they are also available in the web GUI. Okay, so I already took way too long. Are there any questions?
Actually, you have time. I think we are not over time. But you have 4 minutes presentation still. Yeah?
I still have 4 minutes for the presentation?
I think yes.
Oh,
yeah.
okay.
Oh.
Yeah, okay.
Hello. While you were explaining about the project, I paid a visit to the website and I saw that you are interested right now in doing a data plane, how it's called, the data software data plane, correct? I was reading recently about this and I was interested for something of my own. And I would actually like to know how would you do this software data plane, but you need to explain to me actually what is this software data plane, because I was actually learning about it nowadays. So I see it as a great opportunity to learn about it. And I'm asking since there isn't any other question. Thank you.
I'm sorry, what do you mean by data plane?
It's just written in your website, basically, and you say that I will tell you exactly what you write here, and you're writing, following the completion of the initial version, a comprehensive software development plan will be established for the full version.
I didn't get it, I'm sorry.
Fine, it's fine. Okay, thank you still. Thank you. It's fine. Thank you.
Yeah, I didn't get the question. I'm sorry.
There seems to have been a misread of software data plan or software development plan as software data plane. It's a different thing. It was a misread.
Okay, yeah.
I do have a question. So you decided, thank you for the presentation first of all, you decided to run Java via Python, if I understood you correctly, because you said it's good to avoid the back and forth, and so you do the loops in Java and you return the data in Python. I was wondering if you're gonna do that, isn't it more meaningful to have a
a server architecture where you run things in Java and you can send it data to process and then you poll it for the answers. So you have something running and you don't have to start it and stop it through Python.
That's a very interesting point, and I think there's a project using ORCID that does exactly that. I forgot the name, but basically it runs Java in the back end, and then you get some data via API. First, it's a bit less flexible because you need to just define the data exchange via the API. And second, the requirement was to have Ephemerista both as a web service, as an API, and as a library. So we had the requirement to be able to run everything in Python. But if we were to develop software as a service, so completely deployed as a web, it would have been maybe a possibility. Yes.
Just one question. Would it be possible, or did you think about also calculating the optical magnitude of satellites, which could be interesting for observation, or maybe, I don't know, the RF cross-section or something? And then the second question is, does it make sense to benchmark this also to Stellarium or something, and not MATLAB?
For the first part, it would be an interesting feature, and you are free to contribute, or at least to open an issue ticket on the GitLab, and then maybe someone will develop it. It's definitely possible using either the ORCID backend or the Rust backend. The second part, I don't remember exactly what Stellarium does, but is it only visualization or also propagation? Because we do much more than only visualization. But for the benchmark part, we did a bit of benchmarking, but I don't remember against which tools and what were the results, because it's quite hard to have equivalent, to be able to compare it like to softwares like SDK. They are GUIs, and they're expensive, so you need to get your hands on it and then to do exactly the same configuration, because there are like really tens of parameters that you need to set the same, like the numerical propagator, the spacecraft properties, etc., the transformation, like the coordinate frame. So it's quite hard to have one-to-one comparison between tools. But we could maybe do some benchmarks against other libraries in Python. That would be interesting.
Yeah, so one thing, have you considered doing what's called like satellite-to-satellite connections in your link budget simulations?
Sorry, say again?
That's like you showed the link budget simulation for ground station to a satellite connection. Have you considered doing it for one satellite to another?
I think we do already. I have to check, but I think you can just use two spacecraft assets and just tell one to track the other, and then compute some link.
Oh, amazing! Yeah.
Okay, I think we're done. Yeah. Thank you.
Thank you.
So this was a last presentation for today. See you tomorrow at 9 and today at 8 o'clock at Hackerspace, the social event. So thank you very much for being here. Freddy says that I need to say that tomorrow we have a DST change. Yeah, DST, daylight saving time, yeah. So, yeah, be aware of that. Like, yeah. I assume that your, I don't know, cell phone will do it automatically, yeah, but, yeah. For the last time? Yeah, for the last time again, yeah, like, I've lived like 20 last times again, yeah. Okay, so see you later and tomorrow, yeah. Thank you.
Απλά να κλείσουμε το υπολογιστή από εδώ.
Και θα κλείσουμε το όνομα του Σεράφης. Αυτό λέω.
Εδώ είναι όλα κλειστά.